Hello. We're glad you are here. Wherever you are right now, lie in the quiet of your room or somewhere soft and still. You have done something rare and good. You have set everything down. The lists, the tasks, the small worries that follow us through our days. You have set them all down. Tonight, we go somewhere much larger than all of that. We are going to the edge of the universe. Not quickly, never quickly. We will move the way light moves when it is all the time in the universe to arrive, which, as it turns out, it does. We will move through the dark and the vast and the silent, and we will let the sheer, unhurried enormity of it all settle over us like something heavy and warm. There is nothing you need to hold on to. There is no plot here. Nothing will startle you. No loud sound will come. Only the slow, slow turning of the cosmos and our voices moving gently through it together. Let your shoulders rest. Let your jaw loosen. Let your eyes, if they wish to close, close. We are going a long way tonight, and we have all the time in the world. For as long as human beings have existed, long before the first written word, long before the first city rose from mud, we have looked up on every continent, in every age, in every language that has ever been spoken. We have pressed our backs against the earth and looked up at the sky above us and felt something that is very hard to name, something that sits between wonder and smallness, between awe and peace. The ancient Egyptians watched the stars to measure their floods and know when to plant their grain. The sailors of Polynesia read the sky the way we read a map, and crossed thousands of miles of open ocean, using nothing but the light above them. The astronomers of ancient Mesopotamia lay awake through long desert nights, cataloging the wandering points of light, giving them names, watching them move, trying to understand. We are still trying to understand. What we have learned, slowly and painstakingly, and with great effort over many centuries, is something that would have overwhelmed every one of those ancient sky watchers entirely. Something so large that even now, even with all the mathematics and all the telescopes and all the time we have spent studying it, it does not really fit inside the human mind. The universe is almost incomprehensibly large, and tonight we are going to travel through it together. From here, from Earth, outward, past everything we can name, past everything we can see, all the way to the very edge of what is knowable, to the horizon beyond which even light itself has never reached us. We will take our time. We will pause often. We will let the distances wash over us without hurrying to understand them. Because the deep truth about the universe is this: it rewards patience. It rewards stillness. It has been here for nearly 14 billion years, and it is not going anywhere. And neither, for a little while, are we. We begin, as all great journeys begin, at home. Stand outside on a clear night and look up. Now imagine looking in every direction at once, north, south, east, west, straight up to the roof of the sky, straight down to the floor of the earth. Imagine looking in every direction simultaneously, outward in a perfect sphere from the exact point where you are standing. What you would see In every direction, if your eyes could reach far enough, is the same thing, a wall of ancient light. The observable universe is a sphere, and we are at its center, not because we are special, not because we occupy some privileged position in the cosmos, but simply because we are here, and light can only have reached us from a certain distance in the time the universe has existed. Look north, and eventually at the very edge of seeing, you'll find the oldest light there is. Look south, the same. Look in any direction across the infinite dark, and the boundary is always the same distance away, always the same age, always the same faint, ancient glow. We live inside a perfect sphere of knowable space, and everywhere you look, the sphere is equally deep. There is something extraordinarily calming about this. We are held in every direction by the same ancient light. We are surrounded equally and completely by the same vast dark. There is no edge that is closer or further than any other. In every direction, the same quiet, the same depth, the same slow drifting dark. Here is something worth holding gently in your mind as you rest. Wherever you are in the universe, wherever any being, anywhere in the unimaginable expanse of creation happens to be, they see the same thing, their own sphere, their own horizon, the same depth in every direction, the same ancient boundary all around them. The cosmic horizon moves with whoever is observing it. If you travel for 1 billion years to the far side of the Milky Way and looked out from there, you would still find yourself at the center of your own observable universe. The horizon would be just as far away. The same sphere would surround you, with you at its heart. You would not have gotten any closer to the edge. There is no place in the universe that is closer to the edge than any other place. There is no place further from the center. Every point is the center. Every observer stands in the middle of their own enormous, equally sized sphere of knowable space. The universe has no edges you can reach. It has no walls you can press your hand against. It surrounds every possible observer equally and everywhere. It is equally and softly and permanently full of the same ancient quiet. Close your eyes for a moment. If they are not already closed, you are at the center of the universe right now. You have always been at the center of the universe. You will always be at the center of the universe, not metaphorically, cosmologically, truly and precisely and without exception. Now we must talk about something that takes a little while to settle, which, appropriately, is exactly what we have. The universe began approximately 13.8 billion years ago, and the light at the edge of what we can see, the very oldest light, the most distant glow we can detect, left its source at almost exactly that moment. It has been traveling ever since, through unimaginable space, through cold and dark and expanding void. For 13.8 billion years, it has been on its way to us, and now it is here. But here is the quiet strangeness. The place that light came from is no longer where it was. Space itself has been expanding this whole time, not like an explosion scattering things outward, but like the very fabric of distance stretching, like a slowly inflating fabric woven through everything. And because space has been expanding, the source of that ancient light has been moving away from us, not through space, but with it, carried along on the stretching fabric of the universe itself. The light that left its source 13.8 billion years ago came from a place that is now, by our best measurements, approximately 46 billion light years away. It left from nearby. It arrived here after an almost incomprehensible journey, and the place it came from has, in the meantime, drifted nearly 46 billion light years away from us, still moving, still receding, carried on the silent expansion of the universe that never stops and never slows. Everything is drifting, everything is expanding, and yet here we are, perfectly still, at the center of it all, held in place by nothing more than the soft weight of sleep and the hum of the dark around us. We tend to think of the speed of light as an absolute limit, and, in a sense, it is. Nothing can move through space faster than light, but space itself is not subject to that rule. The galaxies at the very edges of our observable universe are receding from us at speeds that exceed the speed of light, not because they are racing away through space, but because the space between us and them is stretching. New distance is being created constantly in every gap between every galaxy, every cluster, every quiet filament of the cosmic web. And that creation of new distance can happen, and at the edges of our universe does happen, faster than light can cross it. Those distant galaxies are not racing. They are drifting. They are doing nothing at all, in a sense, just sitting in their small patches of space, around which stars are slowly burning, around which planets may be quietly turning. They are not moving. The space between us and them simply keeps getting larger. This means that no matter how long we wait, no matter how advanced our telescopes become, we will never see those galaxies. The light they're sending toward us right now will never arrive. The distance between us grows faster than the light can cross it. They are beyond our horizon, not because they are hidden, but because the universe itself is pulling the ground out from under every photon they send our way. There is a gentleness to this. Somehow, not loss, not absence, just a quiet acknowledgement that the universe is very large, larger than sight, larger than reach, larger than light. And we are here at our center, held in our sphere, at rest, the observable universe. Our sphere, our horizon, our 46 billion light-year bubble is not the whole universe. It is only the part we can see. And some cosmologists believe that beyond our horizon, the universe continues, not for a little while, not for a few more billion light years, but forever, infinitely. An unbounded expanse of space that goes on and on without limit, without wall, without edge, without end. If this is true, and we do not know for certain that it is, but if it is, then something remarkable and rather strange follows from pure mathematics. If the universe is infinite, and if matter is distributed through it in roughly the same proportions we see here, then every possible arrangement of matter must occur somewhere. Every pattern, every configuration, somewhere unimaginably far beyond our horizon, there must exist a region of space arranged in almost exactly the way our region is arranged, with a galaxy like ours, with a solar system like ours, with a planet blue and quiet, orbiting a yellow star. And on that planet, in that unimaginably distant region, there may be a room arranged very much like yours, and a person lying very much like you are lying, listening to something very much like this. We cannot visit them. We cannot communicate with them. We will never know. But the mathematics does not forbid it. The mathematics, in a sense, insist upon it. If the universe is truly without end, let that thought drift. Let it go where it wants to go. Somewhere out beyond the darkness and the expanding void and the ancient light. Something is very much like here. Something is very much like now. Something is, perhaps, very much like you, growing still and heavy and quiet in the dark. Human beings, for all that we sometimes forget it, are remarkable dreamers. We cannot travel to the edge of the universe. We do not have the time. We do not have the speed. No spacecraft we could build, no engine we could conceive, no fuel we could carry would ever be sufficient for a journey of 46 billion light years. Even if we could travel at the speed of light, even if we could somehow move as fast as anything in the universe is permitted to move, we would still be traveling for 46 billion years. And yet, we wanted to see it, using data collected by the Hubble Space Telescope, that extraordinary instrument, drifting quietly in its orbit above our atmosphere, gathering light from across the cosmos. Scientists and visualization artists created something extraordinary, a simulation, a continuous, unbroken, computer-generated journey from the surface of the Earth outward, through the solar system, through the galaxy, through the great clusters and superclusters and voids of the cosmic web, all the way to the furthest wall of ancient light, the cosmic microwave background, the faint afterglow of the universe's first moments. No cuts, no jumps, no sudden transitions, just a slow, continuous unfolding of scale. Earth becoming a marble, the solar system becoming the Milky Way becoming a smear of light, the local group of galaxies becoming a small cluster among thousands, the thousands becoming hundreds of thousands, the hundreds of thousands becoming a faint web of filaments stretching toward the horizon. Someone sat down and made that journey, frame by frame, with great patience and great care, so that the rest of us could watch, so that we could close our eyes and feel the distances, so that we could travel without moving. We're doing something similar tonight, moving through all of it together at the slowest possible pace. Scale is the hardest thing to hold on to when we think about the universe. Our minds were shaped by evolution to navigate a world of trees and rivers and distances you can walk in a day. We are simply not built to feel the difference between 1,000,000 and 1 billion, let alone 1 billion and 1 trillion. So we use models, comparisons, shrinkages. Let us try one together now. Imagine that we shrink the entire solar system, the sun all 8 planets, everything from the scorching surface of Mercury to the cold, slow drift of Neptune, down to the size of the Earth, 12,700 kilometers across. A sphere you could walk around the equator of in a little over 40 days. At that scale, the Milky Way, our home galaxy, the slow spiral of 200 to 400 billion stars, would be a disk approximately 16 meters wide, about the size of a small room, about the span of a single-story house. So the entire solar system, shrunk to the size of our planet, would fit within a single room inside our galaxy. And the observable universe? The whole sphere, all 46 billion light years of it, with its 2 trillion galaxies and its incomprehensible dark, at that same scale, it would be approximately the size of a football stadium. A stadium with a 16-meter room inside it, somewhere which contains our scaled-down Earth. And on that Earth, somewhere there's a room. And in that room, there is something the size of a single hydrogen atom. And that is you, and you are right now at the exact center of the stadium. Let that settle for a moment. Let it simply rest there without needing to mean anything. You at the center of a stadium-sized universe. Perfectly still, growing quieter, very, very small in the most beautiful and peaceful way. When we make our journey tonight, our slow, unhurried passage from Earth to the edge, we will pass through things that are almost impossible to describe. 2 trillion galaxies, not 2 trillion stars. 2 trillion galaxies, each one a vast, slowly rotating collection of stars and gas and dark matter and dust bound together by gravity, drifting through space on its own long, slow path through the cosmos. The Milky Way, our home, is considered a fairly average-sized galaxy. It contains somewhere between 200 billion and 400 billion stars, each one a sun. Many of them, we now know, orbited by planets. Some of those planets, almost certainly the right distance from their star to hold liquid water on their surface. And there are 2 trillion of those. 2 trillion galaxies, each containing hundreds of billions of stars, scattered across the observable universe in an enormous, delicate, filamentary web. And here's the quietest part of this thought. All of that, all 2 trillion galaxies, all the combined billions upon billions of stars, represents only the matter that interacts with light, the matter we can actually see, the matter that glows and burns and shines. The rest of the universe, the dark matter, the dark energy, the structures and forces we can barely detect and cannot yet explain, makes up roughly 95% of everything that exists. What we can see is 5% of what is there. 2 trillion galaxies, each with hundreds of billions of stars, is 5%. Let your mind rest against that number. Do not try to hold it. Just let it wash over you like dark water. 2 trillion. And that is only the shining part, only the surface, only the small fraction that burns brightly enough for us to notice. If you could see the universe from far enough above, If you could somehow float outside it and look down at the whole of it at once, it would look like something alive. It would look like a web. Galaxies are not scattered randomly through space. They cluster. They gather into groups. The groups into clusters. The clusters into superclusters. And those superclusters arrange themselves along vast, thin filaments, threads of matter stretching hundreds of millions of light years across the cosmos, like threads of silk in an unfathomably enormous tapestry. Between the filaments, voids, enormous, near-empty regions of space where very little exists, where the dark between galaxies becomes something even emptier, where the silence is so complete it almost has a texture, and along the filaments, galaxies, billions of them, strung along the threads of the cosmic web like soft lights along a long, dark road. This structure, the cosmic web, fills our entire observable universe. It is not a local phenomenon, not something that exists only nearby. From the very first moments after the Big Bang, tiny fluctuations in the density of matter set the seeds of this pattern. Gravity did the rest, slowly and patiently over billions of years, drawing matter together into threads and knots, leaving the voids emptier and emptier, building the web one slow filament at a time. The universe is not uniform. It is not a smooth sea. It is a web, an intricate, delicate, ancient architecture of matter and dark, stretching from here to the horizon in every direction. And we are on one of the threads, somewhere along a small branch of filament, in a quiet spiral galaxy, on a small blue planet, in a room that is perfectly, completely still. Our first great landmark on this journey is not something bright. It is something empty, just beyond our immediate neighborhood of galaxies, past a local group, past a small collection of gravitationally bound galaxies that includes the Milky Way and our nearest large neighbors. We encounter the local void, a void 150 million light years across. Not a hole, exactly, not a complete absence of matter, but a region where the density of galaxies drops dramatically, where the filament of the cosmic web are thinner or absent, where the dark between things grows very deep and very wide. The local void is not static. It is expanding, growing. The slight underdensity at its heart creates a slightly weaker gravitational pull than the surrounding regions, and so matter at its edges tends to drift away into the denser filaments beyond. The void slowly empties itself, becomes quieter, becomes more itself. We live on the edge of this void. The Milky Way sits at the boundary between the local void and the denser filaments of the Lania Chaos supercluster. The vast structure, 500 million light years across, of which our galaxy is a very small part. We are, in a sense, at the shore of an enormous, slowly growing emptiness, looking in from the edge. On one side, the soft glow of billions of galaxies woven along their filaments. On the other, the deep, slow dark of the void, expanding outward into itself. It is very quiet at the shore of a void. It is very quiet everywhere. Out here, let yourself feel that quiet. Let it come in. Let it settle alongside the hum of the drone and the wave of your own body. And let everything slow, as the universe itself is always slowly slowing. We are moving now, not quickly. We have promised ourselves we will never move quickly tonight, but moving past the shore of the local void, outward into the larger architecture of the cosmos. And as we travel, we begin to notice that the universe, for all its silence, is not entirely still. There are currents here, slow, enormous gravitational currents, tugging at everything that is mass, drawing clusters and superclusters in vast, coherent flows across the dark. The universe breathes. It moves. It has a direction of a kind. Let us feel it as we pass through. The universe, on its largest scales, does not sit perfectly still. Astronomers have measured something they call bulk flow, the coherent, collective motion of enormous regions of the universe, moving together in the same direction, pulled by concentrations of mass so large they can be felt across hundreds of millions of light years. Our own region of space, the Milky Way, the local group, the entire Lonic Chaos supercluster, is moving, drifting, being tugged at approximately 600 kilometers per second toward a vast concentration of galaxies and clusters known as the Shapley supercluster. 600 kilometers per second. In a single second, our entire neighborhood moves 600 kilometers. While you've been listening to this sentence, everything you know has moved thousands of kilometers through space toward a distant gravity, what you will never see with your own eyes. And yet, it does not feel like anything. The motion is so smooth, so vast, so perfectly free of friction and turbulence that it is entirely indistinguishable from stillness. We are falling very slowly towards something enormous, and it feels like lying perfectly still in a quiet room. The Shapley supercluster, the gravitational attractor drawing us on, lies roughly 700 million light years away. We will not arrive in any time frame a human being can conceive. The pull is real and the motion is real, but the destination might as well be a point of stillness on a distant, silent shore. 600 kilometers a second, perfectly still. Both things are true at once in the quiet dark. The filaments of the cosmic web are not empty conduits. They are threaded through with something invisible and ancient, magnetic fields, not the strong, concentrated fields of a planet or a star, but vast, diffuse, enormously extended magnetic fields that stretch across megaparsecs, each megaparsec being just over 3 million light years, woven through the gas and dust and dark matter of the cosmic filaments like a slow, permanent current. These fields are old. They may have their origin in the very first moments of the universe. Tiny fluctuations in the primordial plasma of the early cosmos that seeded the first magnetic structures, which were then amplified and extended over billions of years by the motions of galaxies, the explosions of stars, the slow churning of intergalactic gas. What they do, among other things, is influence the way gas collapses. When a cloud of gas in a filament begins to fall inward under gravity, the the first step toward eventually forming a star. Those magnetic fields resist. They push back. They slow the collapse. They introduce a subtle tension into the process of stellar birth, threading through the gas like a memory of the very earliest moments of creation, still present, still gently pushing. The universe remembers its own beginning in its magnetic fields, in the faint, megaparsec spanning structure of invisible force that runs through everything, ancient, quiet, present, like the hum of something that has always been here, like the drone beneath everything. As we move through the cosmic web, passing from one filament to another, we can begin to notice something in the galaxies around us. They are spinning, not randomly, not in directions chosen by chance. The rotation of galaxies, the slow, billions of years-long turning of their disks, is influenced by the gravitational environment in which they formed. In particular, by the tidal forces exerted by the large-scale structure around them. Tidal torque, the same force that stretches ocean water toward the moon, that raises and lowers the tides on every coast on Earth, operates across cosmic scales. When a galaxy is forming, when its cloud of gas and dark matter is slowly condensing under gravity, the gravitational pull of the surrounding superclusters is not perfectly uniform. One side pulls slightly more than another. The forming galaxy responds, acquiring a tiny rotation, and then, over billions of years, as it collapses and cools and becomes a disk of stars, that tiny rotation is amplified into majestic, slow spiral we see today. Every spiral galaxy in the universe was spun up, in part, by its neighbors, by the uneven tug of the vast structure around it, by the tidal whisper of the cosmic web itself. The Milky Way turns because the universe around it pulled it gently on one side more than the other billions of years ago, and it has been turning ever since. Slowly, permanently, without friction, without end. The filaments we are traveling through are not made primarily of stars. They are made of something we cannot see, dark matter. The word makes it sound like an absence, like darkness, like nothing. But it is not nothing. It is something, and it has mass. And that mass creates gravity, and that gravity shapes everything. We just cannot see it. It does not emit light. It does not absorb light. It does not interact with the electromagnetic spectrum in any way that our instruments can detect. It reveals itself only through what it does to the things around it, through the way it bends the paths of galaxies, through the way it holds clusters together against the centrifugal forces that should, by rights, fling them apart. The filaments of the cosmic web that we are traversing tonight are, at their core, filaments of dark matter, the visible galaxies, the glowing points of light strung along the threads like soft lanterns on a long, dark road, are only there because the dark matter was there first. It collapsed into filaments, slowly, under its own gravity. And the ordinary matter, the gas that became stars, the stars that became galaxies, followed it, settling into gravitational valleys that dark matter had carved. We are traveling through a skeleton, a vast, invisible skeleton of dark matter, draped with a thin sheen of glowing ordinary matter. Everything we can see, every galaxy, every cluster, every bright filament is only the surface of something much larger and much older and completely, perfectly invisible. It is all around us right now, threading through everything, holding everything in place. We cannot see it. We cannot feel it. It passes through us without pausing. The universe is mostly made of things that cannot be seen. Between the filaments, between the glowing threads of galaxies and the warm, invisible scaffold of dark matter, there is something else. There is nothing, or near nothing, the voids of the cosmic web, the enormous, roughly spherical regions enclosed by the filaments, the spaces that the matter has drained away from, are among the largest structures in the universe. Some of them are hundreds of millions of light years across, larger than superclusters, larger than anything made of stars or gas or dust. And as we travel outward from Earth, the voids grow. The nearby universe is clumpy. Lots of structure, lots of variation, lots of bright knots of galaxies and busy filaments. But as we move to larger and larger scales, the voids become more dominant. They fill more and more of the volume of the universe. They are, in fact, the most common environment in the cosmos. Most of the universe, by volume, is void, is near emptiness, is dark. The galaxies and clusters and filaments, all the bright, complex, interesting structure, are crammed into a thin, lacy shell around the surfaces of these voids, like foam on the surface of enormous, dark bubbles. The foam is everything we have ever seen, everything we have ever studied, every galaxy in every photograph ever taken. And the bubbles, the voids, are most of what exists. The universe is mostly empty, mostly dark, mostly void, and the darkness is not threatening. It is simply the natural resting state of space, the default condition of existence, quiet and very, very large. The voids are not static, not fixed, not permanent shapes carved into the universe and left there. They are growing. The expansion of the universe, the Hubble flow, the slow stretching of all distances across the cosmos, applies everywhere. But inside voids, something additional happens. Because the density of matter inside a void is lower than average, the gravitational pull inward is weaker than average. There is less matter pulling things back together, less resistance to the expansion. And so the expansion inside a void runs slightly ahead, approximately 20% faster than the cosmic average. The voids are expanding more quickly than the filaments around them. Their interior distances stretch faster. The already enormous emptiness becomes incrementally, continuously more enormous. A void that is 100 million light years across today will be larger tomorrow, and larger the day after, and larger every day forever, at a rate slightly faster than everything else. This means the voids are slowly consuming the cosmos. As they expand faster, they gradually squeeze the filament between them. The lacy foam of galaxies is being slowly, gently, persistently compressed between the walls of the growing voids, like foam between slowly inflating balloons. In the very far future, billions and billions of years from now, the voids will dominate almost entirely. The filaments will be thin and sparse. The galaxies will be isolated, and the vast majority of space will be void, expanding endlessly into itself. But that is not tonight. Tonight, the web is still luminous. The filaments still glow. We are still surrounded on all sides by the soft light of distant galaxies. For now, the filaments of the cosmic web are not empty conduits either. They are filled with something. Gas. Vast, diffuse, extraordinarily tenuous gas. Spread across millions of light years, shock-heated at temperatures between 100,000 and 10 million degrees. So thin that you could pass through it without feeling anything at all, and yet so extended that in total it contains enormous amounts of matter. Cosmologists call it the WIM, the warm-hot intergalactic medium. The WIM is thought to contain the missing baryons, the ordinary matter that theoretical models of the universe predict should exist, but that astronomers struggle for years to find. It was there all along in the filaments, too hot and too diffuse to see in visible light, but detectable as a faint absorption feature in soft X-ray observations. A ghost presence in the space between galaxies, warm and enormous and all but invisible. We are passing through it right now in our journey. The gas streams around us, or rather, we stream through it, so tenuous we do not even notice. It is heated by the shock waves that arise as matter flows along the filaments, as gas falls down the gravitational slopes of the cosmic web and collides and compresses and heats. The violence of cosmic structure formation, played out in temperatures measured in millions of degrees, contained in a medium so thin it barely exists, hot and invisible and vast and silent. The universe is full of things too large and too thin to see, full of presences that register only as absences, only as faint marks on instruments, only as the ghost of what the mathematics predicted would be there. We are threading through one of those ghosts right now. Galaxies are not permanent. They change, they grow, they collide. As we travel outward through the cosmic web, we pass through regions where galaxy mergers are more common. At intermediate distances, redshifts that correspond to several billion years ago, the universe was more densely packed. Galaxies were closer together, and the rate at which they fell into one another was higher than it is today. The process is not violent in the way we might imagine. Two galaxies approaching each other over millions of years do not crash like billiard balls. The stars within them are so sparsely distributed that individual stellar collisions are vanishingly rare. Instead, the galaxies pass through each other, gravitational tides stretching long arms of stars from each one, drawing out loops and arcs and shells of stellar material. And then, slowly, they are drawn back together, and the process repeats. And each time they pass through each other, they lose a little energy to something called dynamical friction. the mutual gravitational braking of one galaxy moving to the mass of another, and slowly, over many hundreds of millions of years, they spiral together into one. The result is an elliptical galaxy, a smooth, rounded, featureless form. All the graceful spiral structure of both progenitors dissolved and randomized by the chaos of the merger. The most common large galaxies in the densest environments of the universe, built from collisions, built from slow gravitational friction, built from two things becoming one. Somewhere in the sky above us, two galaxies are in the middle of this process right now, taking their time, losing their shapes, becoming something new. As we approach the denser regions of the cosmic web, the clusters, the great gravitational knots where hundreds or thousands of galaxies are bound together, we begin to notice something at their edges, a haze. A faint, diffuse glow that fills the space between the galaxies of a cluster, not bright enough to be any individual star, not concentrated enough to be any individual galaxy, just a soft, pervasive shimmer in the intergalactic space of the cluster, an inner light with no obvious source. This is intercluster light, and its source is some of the loneliest stars in the universe. As galaxies orbit within a cluster, the gravitational tides of the cluster itself can strip stars from the outer edges of those galaxies, pulling them free from their home galaxy and releasing them into the general space of the cluster. These stars become intercluster stars. They no longer belong to any galaxy. They orbit the cluster as a whole, adrift in intergalactic space, belonging nowhere in particular, and together, their combined light creates the soft, diffuse intercluster glow we see at the edges of dense clusters. There are entire stellar populations, billions of stars, living between galaxies, orphaned by gravity, wandering through the intergalactic space of their cluster, lit by no particular dawn, belonging to nothing, contributing their small quiet light to a haze that spreads for millions of light years, adrift but not alone, surrounded always by others equally adrift. Some galaxies carry their history on their surfaces, the way old trees carry their rings, or the way mountains carry the shape of the forces that made them. Shell galaxies, in the outer halos of certain elliptical galaxies, faint arcs of stars are visible, concentric, like the layers of a very old, very slow ripple in a pond. These shells are the remnants of past mergers. When a smaller galaxy fell into the larger one, the stars of the smaller galaxy did not mix evenly. They sloshed, they overshot the center, they spread outward and then fell back, and spread outward again, leaving faint stellar arcs at the turnaround points of their orbits. These arcs persist for billions of years, long after the merger is complete, long after the smaller galaxy has been entirely absorbed. The shells remain, slowly fading, as a memorial to what once was two separate things becoming one. Ring galaxies tell a different story. When a small galaxy passes directly through the center of a larger disk galaxy, like a stone dropped in the middle of a pond, the impact sends a circular density wave rippling outward through the disk. Stars and gas pile up at the crest of the wave, compressing, triggering new star formation, glowing blue with the light of newly born suns. The result is a ring, a bright, expanding circle of stellar birth, spreading slowly outward from the point of impact, while the nucleus of the original galaxy sits quietly at the center, the wound expanding outward from the forever. Galaxies remember. Their shapes carry the record of every collision, every slow merger, every passing encounter. The universe is not just structured, it is scarred, and the scars are beautiful. We have been traveling for some time now. The drone is still here beneath us, low and constant, and the dark continues to deepen as we move outward through the web. We have passed through voids, threaded through filaments of invisible magnetic force, watched galaxies collide in slow motion silence. And now, as we move further from home, we begin to notice something else. The galaxies around us are different here, younger, more restless, still in the process of becoming what they are. We are, in a sense, looking back in time. The further we travel, the older the light we see, and the younger the universe it shows us. Out here, we are watching the cosmos in an earlier chapter of its story, and the galaxies have not yet settled into the forms they will one day hold. At the heart of most large galaxies, there is an engine, a supermassive black hole, millions or billions of times the mass of our sun. Sitting at the very center of the galaxy, bound there by the same gravity that holds the stars in their orbits. Most of the time, it is quiet, sleeping. It sits in the dark and exerts its enormous gravitational presence and does very little else that we can see. But sometimes, especially in the younger universe we're entering now, the deeper paths we're traveling into as we move outward, those central black holes wake up. They begin to feed on the gas and dust that falls toward them, and as they feed, they release energy, enormous energy, far more energy than any star could produce. Jets of plasma and radiation that shoot outward along the axis of the black hole's spin, traveling hundreds of thousands of light years in each direction, out through the galaxy and far into the surrounding halo of gas beyond. And this energy, this outflow, this feedback for what astronomers call an active galactic nucleus, does something profound and permanent to the galaxy it lives inside. It heats the gas that would otherwise cool and collapse and form new stars. The active nucleus pushes it outward, warms it, stirs it, prevents it from condensing, and in doing so, it gradually, over millions of years, shuts down the galaxy's ability to make new stars. The galaxy ages. The blue, restless light of young stars fades. The older, redder stars are what remain. The engine at the heart of the galaxy eventually silences the galaxy itself. A slow, permanent quieting. The galaxy turns off its own lights, one stellar nursery at a time. Further out, deeper into the past, we begin to encounter something remarkable. Regions of space where clusters of galaxies are still forming, where the great gravitational knots of the cosmic web are still tightening, still pulling matter together, still in the process of becoming the dense, glowing clusters that will one day dominate the most massive nodes of the web. These are protoclusters, nurseries of the largest structures in the universe, and at their hearts, in the densest and most active regions, there is sometimes a kind of object we do not see in the local universe, something vast and diffuse and glowing that has no single center and no clear boundary. A Lyman alpha blob, named for the specific wavelength of ultraviolet light they emit, the Lyman alpha line of hydrogen, redshifted by the expansion of the universe into visible wavelengths we can detect. These blobs are among the largest single-emitting structures known. They can extend across 100,000 light-years or more. They glow with the light of hydrogen gas that is being energized, heated and ionized by the radiation from young, massive stars formed within them, or by the output of active galactic nuclei hidden at their centers, or perhaps both. They are vast, luminous, formless pools of glowing gas, seething with the early chemistry of galaxy formation, pour in their substance into the galaxies that are condensing within them. The gas that falls from these blobs into the proto-galaxies at their centers will, over billions of years, become the giant elliptical galaxies that will dominate the richest clusters. Great things, forming slowly in the quiet early dark. As we travel, we notice a change in the character of the galaxies around us. Near home, the universe we are familiar with is populated largely by large galaxies, spirals and ellipticals of significant size, systems containing billions or hundreds of billions of stars, held together by deep gravitational wells, shaped by billions of years of evolution into elegant, familiar forms we recognize from photographs. But as we move outward, as we look further into the past, the dwarf galaxies become more prevalent. Smaller systems, irregular in shape, containing perhaps only a few 100 million stars rather than hundreds of billions. Less organized, more chaotic, more raw, near our cosmic neighborhood. Dwarf galaxies make up roughly 5% of the galaxy population by number, but near the horizon of the observable universe, that fraction climbs to over 90%. In the early universe, dwarf galaxies were not the exception. They were the rule. They were almost everything. This is how large galaxies form. Not all at once, not from a single enormous collapse of gas, but slowly, over billions of years, through the merging of smaller things into larger things. The dwarfs are the building blocks, the raw material, the first galaxies the universe made, before it had the time to assemble them into the larger, more complex structures we see nearby. Out here near the horizon, we are surrounded by the universe in its childhood, small and irregular and restless, still becoming what it will eventually be. Everything begins small. Everything, given enough time, grows. There is a color to time. In the local universe, when we look at the galaxies around us, many of the large ones are red. Their stars are old. The massive, hot, blue stars that burn brightest and fastest have already lived and died long ago. What remains of the older, cooler, redder stars, the long-lived ones, still quietly burning, but giving the galaxy as a whole a warm, reddish, autumnal glow. These are quiescent galaxies, still galaxies, no longer actively forming new stars in significant numbers. Their story, in terms of stellar birth, is largely complete. But further out, deeper into the past, the galaxies are bluer, livelier, still forming stars in abundance, still rich in the cold gas that condenses into stellar nurseries, still populated by the young, hot, massive stars whose blue-white light floods out across the surrounding space. Astronomers describe this as the red sequence and the blue sequence. Galaxies begin blue, star-forming, restless, luminous, and gradually, over billions of years, transition to red. The blue fades. The nurseries close. The last massive stars burn out and are not replaced. The galaxy settles into a long, quiet, red old age. We are watching this transition in reverse as we travel, moving from the red, settled, elderly galaxies of the local universe, outward into blue, restless, forming galaxies of the earlier cosmos, like watching autumn reverse into spring. The universe was young once, bright and blue and still becoming. There's a quiet mathematics to the shape of a galaxy. When astronomers look at how the brightness of a galaxy changes from its center to its outer edge, how the light is distributed across its face, they find it follows a precise mathematical form. A curve, steep at the center, falling away more gradually toward the edges. And the steepness of that curve, described by a number called the Circic Index, tells them something fundamental about the galaxy's history. A low Circic Index means the light is spread broadly, relatively uniformly. A disk, a galaxy that formed gradually from gas cooling into a rotating plane, never significantly disturbed, never violently merged with anything. A spiral galaxy, seen in profile, has a low Circic Index. A high Circic Index means the light is strongly concentrated toward the center. A bulge, a galaxy whose stars have been stirred and randomized by mergers, whose rotation has been disrupted, whose disk has been dissolved into a more spherical, centrally concentrated form. An elliptical galaxy, born from collision, has a high Circic Index. As we travel outward, the Circic Index distributions of the galaxies around us shift. The average galaxy becomes more disk-like in the distant past, less bulge-dominated. The mergers that will eventually transform so many of these disks into ellipticals have not yet occurred. The shapes are still clean, still undisturbed, still describing the slow, quiet rotation of gas that has not yet collided with anything. A number, a curve, the entire history of a galaxy's collisions, encoded in the shape of its light. Look at a spiral galaxy face-on, and you will sometimes see something unexpected at its center. Not just a nucleus, not just a bright point, but a bar, an elongated, straight, or slightly curved structure of stars, crossing the center of the galaxy like a bridge, with the spiral arms emerging from its ends rather than directly from the nucleus. Bars are remarkable structures. They form spontaneously from disk instabilities, small perturbations in a rotating stellar disk that grow over time into self-reinforcing elongated structures, channeling gas toward a galaxy's center, feeding star formation and sometimes a central black hole. They are not accidents. They are a natural consequence of disk dynamics. Given the right conditions, a rotating disk of stars will generate a bar on its own, without any external trigger. But those conditions change over time. And as we travel through cosmic history, the fraction of spiral galaxies that host bars rises and falls. There are epochs when disk instabilities were more common, when the conditions for bar formation were more widely met, and the bar fraction is higher, and other epochs, earlier or later, when the conditions were different and fewer disks developed bars. These rising and falling fractions are a record of the internal dynamics of galaxies across cosmic time. A subtle, quiet signal, written in the shapes of hundreds of thousands of spiral galaxies, telling us about the instabilities and flows that shape them from within. The bars turn slowly. Everything turns slowly out here. Everything takes its time. Orbiting many large galaxies in loose swarms that extend far beyond the visible disk, they're the globular clusters, dense, spherical collections of stars, typically between 10,000 and a million stars, packed into a sphere only a few dozen light years across, held together by their mutual gravity, orbiting the parent galaxy on long, slow, eccentric paths that take them out into halo and back again over hundreds of millions of years. Globular clusters are among the oldest objects in the universe. Many of them formed in the very early history of their galaxies, or were acquired when smaller galaxies merged into the larger one. They are fossils, preserved remnants of conditions that no longer exist. Their stars formed from gas with a very low metallicity, very few elements heavier than hydrogen and helium, because the universe had not yet had time to make them. These ancient, metal-poor clusters survived when the gas clouds they formed from dispersed long ago survived when the small galaxies they once belonged to were absorbed, survived billions of years of radiation and gravitational perturbations. As we travel outward, the globular cluster systems we observe around galaxies grow thinner. The rich, complex systems of large nearby galaxies, accumulated over billions of years of mergers, give way to the sparser, more primitive systems of smaller and younger galaxies in the earlier universe. But the metal-poor ones, the oldest, most ancient clusters, persist, outlasting nearly everything else. Still turning, still dense, still holding their ancient stars together in the quiet dark. Some things last. The universe, when it was new, contained almost nothing but hydrogen and helium, these two lightest elements. The simplest atoms, the most ancient chemistry, were forged in the first 3 minutes of the universe's existence in the extraordinary heat and density of the Big Bang. Hydrogen, helium, tiny traces of lithium, and almost nothing else. Everything else, every other element in the periodic table, had to be made later, inside stars, In the nuclear furnaces at stellar cores, hydrogen fuse into helium, helium into carbon, carbon into oxygen, and on to the heavier elements, all the way up to iron. And when massive stars exhausted their fuel and exploded as supernovae, those heavy elements were scattered into the surrounding gas, enriching it, making it more complex, giving subsequent generations of stars and planets more to work with. This process of enrichment, called chemical evolution, has been running for nearly 14 billion years, and its progress is written in the metallicity of the gas and stars we observe throughout the universe. Near the horizon, the universe is young and pristine. The gas is close to its original composition, mostly hydrogen and helium, with only the faintest traces of anything heavier. The first stars have only just begun their work. Midway through our journey, the metallicity rises. Multiple generations of stars have lived and died. The gas has been enriched. The building blocks for rocky planets, for complex molecules, for the chemistry of life, are present in significant quantities. We are made of the later universe, of enriched gas, of elements forged inside stars long dead. We could only have formed here, in the mature, metal-rich universe, and not near the horizon, where the chemistry was still almost entirely light. We are very close to the horizon now. Looking back almost at the beginning, and among the stars we encounter in the oldest galaxies, there is a peculiar population. Stars are almost as old as the universe itself. Low-mass stars have formed in the very early cosmos from gas that had been touched just barely by the very first supernovae. Their spectra are strange. They have very low metallicity overall, close to primordial, but with a curious enhancement of carbon relative to other heavy elements. Carbon-enhanced metal-poor stars, CMP stars. Their unusual chemistry is a fingerprint, a signature left by the particular type of supernova that enriched the gas they formed from. Likely the death of a very massive first-generation star, a kind of star called a population 3 star, whose characteristics and explosive end left a distinctive mark on the surrounding gas before any subsequent stellar generations could dilute or overwrite it. These ancient stars are not common, but they exist. They are still burning. Low-mass stars can burn for longer than the current age of the universe, and some of them, formed in the first billion years of cosmic history, are still quietly fusing hydrogen in their cores, still emitting their faint light, still here. They are the memory of the very first stars the universe ever made, the light of the earliest chemistry, the echo of the first deaths, still audible, still visible, in the quiet old stars we find today. Something from the very beginning of everything, still here, still shining, still slow. Not everything in the universe changes with time. Some things simply persist, unchanged, unperturbed, carrying within them the conditions of a much earlier universe, sealed away from the processes of evolution and enrichment that have transformed everything around them. Ultra-diffuse galaxies are one such thing. They are enormous, sometimes as large as a Milky Way in physical extent, but almost invisible. Their stars are spread so thinly across such a vast volume of space that their surface brightness is hundreds of times lower than a normal galaxy. They are ghost galaxies, present but barely there. Some of them appear to contain very little dark matter, which is deeply puzzling, since dark matter is thought to be the scaffold on which all galaxies form. Others contain enormous amounts. They come in different flavors of strangeness, and none of them fit neatly into our standard picture of how galaxies should form and evolve. Fossil groups are another such relic. When a group of galaxies merges, the individual galaxies eventually coalesce into a single large elliptical at the center, surrounded by a vast halo of hot gas, the remnant of all the gas that once belonged to the individual group members. This merged system, with its single dominant central galaxy and its ancient gas halo, can persist for billions of years without significant change. A fossil, a record of a merger that happened long ago, frozen in its aftermath. These objects, ultra-diffuse galaxies, fossil groups, ancient relics of early formation, are like windows into the past. They did not get the memo about evolution. They simply stayed as they were, slowly orbiting in their clusters, preserving in their structure the conditions of an earlier and quieter universe. The universe is full of things that were left behind by time. Ancient, quiet, still, we move gently past them and continue outward. We have been traveling for a long time now. The galaxies around us have changed in character. Smaller, bluer, more restless. And the universe we are passing through is younger than the one we left behind. The dark feels different here. Warmer, perhaps more active. There is more happening in this earlier cosmos than in the quiet, settled neighborhood we call home. We are approaching a threshold, a moment in cosmic history that astronomers call cosmic noon. The time when the universe was making stars faster than at any other point in its existence. When the quasars blaze at their brightest. When the intergalactic fog was burning away. When everything was, in some sense, becoming. Let us move through it together, slowly, without hurrying past any of it. Not everything in the universe moves slowly. Deep in the heart of galaxies, at the very center, where the gravitational field is most intense, where stars orbit in tight, fast paths around the supermassive black hole that lives there, something occasionally happens that launches a star out of the galaxy entirely. When a binary star system, two stars orbiting each other, passes too close to the central black hole, the gravitational interaction can be violent. The black hole captures one of the stars, pulling it into a tight orbit or swallowing it entirely. And the other star, freed from its companion, and given an enormous gravitational kick in the process, is flung outward at extreme velocity, hundreds of kilometers per second, sometimes more than 1,000. These are hypervelocity stars, and they are fast enough to escape their galaxy entirely. They streak out to the galaxy's disk, through its halo, and out into the intergalactic void beyond. Alone, moving fast enough that the galaxy's gravity cannot pull them back. traveling through the dark between galaxies on a one-way journey to nowhere in particular, with no destination, no gravitational anchor, nothing ahead of them but the void. They will travel through that void for billions of years, perhaps forever, moving at hundreds of kilometers per second through the deepening dark, growing ever more distant from the galaxy that made them and discarded them, growing colder as their fuel slowly depletes, until finally their light goes out, somewhere in the middle of nowhere, in the vast quiet between things. Some journeys have no destination, only the moving, here, right here, in the region of the universe we are passing through now. Something is happening that will never happen again at quite the same scale. Stars are being born at a rate that has never been matched before and will never be matched again. Galaxies across the cosmos are filled with star-forming regions, vast clouds of gas and dust, compressing, collapsing under gravity, fragmenting into stellar nurseries, igniting with the light of thousands of new suns simultaneously. The cosmic star formation rate, the total number of new stars being created per year across the entire observable universe, is at its peak, its absolute maximum. The universe, at this moment in its history, is making more stars than it has ever made or ever will make. Astronomers call this cosmic noon. It occurred approximately 11 billion years ago, roughly 2.5 billion years after the Big Bang. The universe was young. The gas was abundant. The conditions for star formation were everywhere, and the rate of stellar birth across the cosmos reached a crescendo that has been declining ever since. Since cosmic noon, the universe has been gradually winding down. The gas in galaxies is slowly depleted. The star formation rate falls, decade by decade, billion year by billion year. The universe today makes stars at perhaps 1/10 the rate it did at cosmic noon. We are passing through the universe's most creative moment, the peak of its generative power, the brightest hour of a day that has been slowly dimming ever since. There is a kind of beauty in being here for this, even in passing, even at this pace. Before cosmic noon, and in the early stages of it, the universe was not fully transparent. After the Big Bang, the cosmos was initially a plasma, so hot that electrons and protons could not combine into neutral atoms, and light could not travel freely without being scattered. Then, approximately 380,000 years after the beginning, the universe cooled enough for neutral hydrogen to form, and the plasma became a gas. Light could suddenly travel. The universe became transparent for the first time. But that neutral hydrogen, the fog of unionized gas that filled the space between the first galaxies, became a new kind of obstacle, a different kind of fog. And as the first stars and the first galaxies and the first quasars began to shine, their ultraviolet light began to ionize that surrounding hydrogen, to strip the electrons from the atoms, to slowly burn the fog away. This process, the epoch of reionization, was driven in large part by quasars, those blazing active galactic nuclei, at their peak density around cosmic noon, poured out torrents of ionizing radiation. Their light reached out across millions of light years, creating expanding bubbles of ioneous gas that gradually grew and merged until, eventually, the intergalactic medium was fully ioneous and the last of the fog was gone. The universe burned itself clear, used the light of its own most luminous objects to dissolve the haze that obscured its own depths. And the sight lines opened, and the cosmos became the transparent, clear medium through which light now travels freely all the way to our eyes. We are passing through the moment that cleared the view, the moment the universe became visible to itself. A quasar is a galaxy whose central black hole is consuming matter at a prodigious rate. Not quietly, not passively, but ravenously. The gas and dust and disrupted stars falling into black hole heat to extraordinary temperatures as they spiral inward, forming a flattened accretion disk that glows with the intensity of trillions of suns. A single quasar can outshine its entire host galaxy, all hundreds of billions of stars, by a factor of 1,000 or more. From across billions of light years of space, it appears simply as a brilliant, almost star-like point of light, a quasi-stellar object, a quasar. And at redshift 2, approximately 10 billion years ago, as we are passing through now, they were everywhere. The conditions were perfect for quasar activity. Galaxies were still gas-rich. Mergers were common. Each major merger funneled enormous quantities of gas toward the central black holes of the galaxies involved, triggering episodes of intense accretion. The black holes fed, the accretion disks blazed, and the quasar density across the observable universe reached its peak, hundreds of times higher than it is today. Today, quasars are rare. The gas has been depleted. The mergers are less frequent. The great black holes at the centers of galaxies have, for the most part, returned to their quiet, sleeping state. The universe's most brilliant chapter of active feeding is over. But here now, as we pass through redshift 2, the quasars blaze on all sides. Brilliant, numerous, ravenous, the universe at its loudest. And we pass through it in silence, as we pass through everything, moving slowly, undisturbed, as we move through the starburst galaxies of the cosmic noon era. There's a particular color of light that tells us where the action is. Red, not the red of age and cooling, not the red of an old, dying star, but the specific, precise red of a hydrogen atom emitting a photon as one of its electrons drops from the third energy level to the second, a wavelength of 656 nanometers, a color called H-alpha. When a massive young star is born, its ultraviolet light floods out into the surrounding gas cloud, stripping electrons from hydrogen atoms, ionizing them. And when those electrons eventually recombine with their protons, they emit light at specific wavelengths as they cascade down to the energy levels of the atom. H-alpha is the brightest of these recombination lines. It traces with extraordinary precision the locations of ioneous hydrogen gas, which means the locations of young, massive stars and the stellar nurseries that produce them. Look at a starburst galaxy in H-alpha, and it lights up like a map of creation. Every star-forming region glowing red, every nursery marked, every site of new stellar birth illuminated in that specific, ancient red wavelength of recombining hydrogen. In the starburst galaxies we are passing through at cosmic noon, H-alpha blazes. The entire galaxy is threaded with it. Stars are forming everywhere, and the gas around them glows red with the light of electrons finding their way back to their protons in the hot, bright, newborn regions of the early universe. A specific red, the color of beginning. How do we know how fast the universe is expanding at different points along our journey? One answer lies in a particular kind of galaxy that appears at intervals throughout the cosmos. Old, massive elliptical galaxies, systems that stopped forming stars long ago, whose stellar populations have been evolving passively ever since, growing steadily older and redder at a rate that is determined entirely by stellar physics, which we understand very well. These galaxies are cosmic chronometers, because we know how quickly their stellar populations age, how fast the color and spectrum of an old, passively evolving stellar population changes over time. We can use the difference in age between two such galaxies at slightly different distances to measure how much time elapsed between them. And comparing that elapsed time to the difference in their redshifts gives us a direct measurement of the expansion rate of the universe at that point in cosmic history. No assumptions about the geometry of the universe, no model dependencies, just a clock written in the aging of old stars. As we travel, we pass these ancient galaxies at intervals, each one a clock, each one a measurement, each one quietly recording, in the slow reddening of its stellar populations, the passage of cosmic time. They do not know they are clocks. They are simply old and still and red, but their stillness is information. Their age is a measurement. Their quietness tells us something precise and important about the history of the expanding universe. Let us pause here and take stock of where we are. The universe is approximately 13.8 billion years old. We began our journey at the present day and have been moving outward, which is the same as moving backward in time. Cosmic noon, which we had just passed through, occurred approximately 11 billion years ago. That means we have crossed more than 11 billion years of look-back time. The remaining journey, from cosmic noon to the furthest horizon, to the edge of the observable universe, covers the remaining 2.5 billion years of cosmic history. From cosmic noon all the way back to the moment of recombination, approximately 380,000 years after the Big Bang, where the oldest light we could detect was released. This is a curious asymmetry. The first portion of our journey, from now back to cosmic noon, covers 11 billion years of time, but represents a relatively modest fraction of the total distance in light years. The second portion, from cosmic noon to the edge, covers only 2.5 billion years of time, but spans an enormous fraction of the remaining cosmic distance, because in those early years the universe was so much smaller and denser that even small differences in redshift correspond to very large physical distances. Look-back time is not the same as distance. The universe was smaller then. Things were closer together, and the light from that compressed early cosmos has been stretched by billions of years of expansion into the long, faint wavelengths we detect today. We are approaching the compressed, ancient, small universe now, moving into the part of the journey that covers the least time but the most territory. The galaxies we see near the edge of the observable universe are not a representative sample of the galaxies that existed there. They are the brightest ones, the most massive ones, the rarest ones. This is a consequence of what astronomers call galaxy bias. The fact that the most luminous, most detectable galaxies are not distributed randomly through space, but tend to cluster preferentially in the densest regions, the highest peaks of the matter distribution, and near the cosmic horizon, where we can only detect the very brightest objects. Those objects are almost exclusively the rare, extreme peaks, massive protoclusters, the most luminous quasars, the most intensely star-forming galaxies. The vast majority of galaxies in the early universe, the small, dim, ordinary ones, are invisible to us from this distance, too faint, below our detection threshold. We see only the exceptional, only the extreme, only the object that were unusual even by the standards of their own time. It is a kind of observational bias built into the physics of detection. We look deepest and see the rarest things. The universe near the horizon looks dominated by massive structures, not because those structures were typical, but because they're the only things bright enough for us to find. The ordinary early universe, the vast, dim, unremarkable majority, is invisible to us. It is there, but it does not reach us. We see the peaks of the early cosmos and imagine the planes we cannot see. The space we are traveling through is not flat. It is curved, not dramatically, not in ways that are perceptible to any instrument aboard an imaginary spacecraft moving through it, but in subtle, measurable ways. The gravity of the matter we pass near, the clusters, the filaments, the concentrations of dark matter along the cosmic web, bends the paths of the light coming from the galaxies behind them. This is gravitational lensing. The prediction by Einstein that mass curves space-time and that light, following the curved geometry of space-time, will appear to bend around massive objects. And near the horizon of the observable universe, where we are trying to see the faintest, most distant galaxies, lensing performs a remarkable service. It magnifies them. A massive cluster of galaxies between us and a very distant background galaxy acts as a natural lens. The gravity of the cluster bends the light from the background galaxy, converging it toward us, making it appear brighter than it would otherwise be. And sometimes, the lensing distorts the background galaxy's shape into an arc, a smeared, stretched, curved image, recognizably different from the circular or elliptical shapes of unlensed galaxies. Cosmologists use this distortion. They look at the statistical distribution of galaxy shapes across a deep field of view, the slight, coherent elongations introduced by weak lensing, and use it to map the distribution of mass, including invisible dark matter, along the line of sight. The shapes of distant galaxies, subtly distorted by the gravity of everything between them and us, are a map of the cosmic mass distribution. The universe maps itself in the curved light of its own most distant objects. There is a strangeness in how we map the universe. When astronomers construct three-dimensional maps of the cosmos, surveys that measure the positions of millions of galaxies across enormous volumes of space. They use redshift as a proxy for distance. The more a galaxy's light is redshifted, the further away it is. In principle, this gives us a three-dimensional map. In practice, it gives us something slightly distorted, because galaxies do not sit perfectly still. Within a cluster, individual galaxies orbit the cluster's center of mass. Some are moving toward us, some are moving away, and because these orbital velocities add to or subtract from the galaxy's cosmological redshift, the galaxies in a cluster appear in redshift space, to be spread out along the line of sight, some appearing closer than they are, some appearing further. The cluster, which in real space is roughly spherical, appears in redshift space as a long, thin elongation pointing directly at the observer, like a finger, like something reaching toward us out of the map. These are fingers of God, named for the eerie pointing shapes that galaxy clusters make in large-scale redshift surveys. They are not physical structures. They are artifacts of measurement, the signature of random orbital velocities smeared out along our line of sight. But there is something quietly wonderful about them. In trying to map the universe, we find the universe pushing back against the map. The gravity that holds clusters together also distorts the way we see them. Our measurements of space are warped by the very structures we are trying to measure. The universe is not easily mapped. It resists simple geometry. It stretches our instruments just as it stretches light. We are very deep now. The universe around us is ancient and young at the same time. Ancient in terms of how long the light has traveled to reach us. Young in terms of how recently this cosmos came into being when this light first left its source. The galaxies are fewer. The structures are rarer. The dark between things is deeper and more absolute. And yet, for all this apparent emptiness, the physics around us is rich. There are waves in the matter. There are pressures in the gas. There are marks left in the distribution of galaxies by sounds that rang out in the first moment of creation and have been frozen in place ever since. We move through it all, slowly, listening. Galaxies do not only move with the expansion of the universe, they also have their own individual velocities, motions driven by the local gravitational environment, by the pull of nearby clusters and filaments and voids. These are called peculiar velocities, and they are largest, as you might expect, in the places where gravity is strongest, the dense hubs of the cosmic web, the nodes where multiple filaments intersect, where hundreds or thousands of galaxies have fallen together into massive clusters, are the most gravitationally intense environments in the universe outside of individual galaxies themselves. The galaxies within these hubs are moving at hundreds or even thousands of kilometers per second relative to each other, falling in, orbiting, passing through, being scattered. These peculiar velocities create the fingers of God we encountered earlier, the elongations in redshift space maps. They also create a kind of kinetic warmth in the most crowded places, a constant agitation, a restlessness that stands in sharp contrast to the deep stillness of the voids just beyond the cluster boundaries. Inside the hub, motion, pressure, turbulence, collision. Outside, nothing. Perfect stillness. The void expanding gently undisturbed. The universe is pockets of intensity, surrounded by seas of absolute calm. The calm is, by volume, almost everything. The intensity is where we tend to look. In the first 380,000 years of the universe's existence, before the cosmos had cooled enough for neutral atoms to form, the primordial plasma was alive with sound. Sound waves, not the sound waves of air and pressure that we know from daily life, but acoustic waves moving through the hot, dense plasma of the early universe, compressions and rarefactions, regions of slightly higher and slightly lower density, propagating outward from every initial fluctuation in the primordial matter. These waves had a particular speed, determined by the temperature and composition of the plasma, and they had a particular lifetime, the 380,000 years between the Big Bang and recombination. At the moment of recombination, when the plasma became neutral gas and photons were free to travel, the sound waves froze. Instantly, the acoustic oscillations stopped propagating. The compressions and rarefactions were locked in place, preserving the distribution of matter as fixed features of the cosmic landscape. The scale of those frozen sound waves is approximately 150 megaparsecs, about 490 million light years. And this scale is imprinted as a slight excess of galaxy pairs separated by that specific distance throughout the observable universe. A preferred scale, a ring, everywhere you look, at every redshift. Galaxies are very slightly more likely to have another galaxy 490 million light years away than you expect by chance. The sound of the early universe, frozen in the positions of galaxies. The universe's first moments, audible as geometry, still present, still here, still measurable. As we continue our journey, the Baryon acoustic oscillation scale keeps appearing. Not once, not as a single ring around a single point of origin, but repeatedly at every distance, in every direction, because those primordial sound waves did not emanate from a single source. They propagated from every point in the early universe simultaneously, from every tiny fluctuation in the primordial plasma, and at recombination, they all froze, all at the same scale, all at once. The result is that the preferred galaxy separation scale of 490 million light years appears at every redshift we can observe. It is the same wave, frozen at the same moment, appearing again and again because it was everywhere when it stopped. A single note played across the entire universe at the same instant, and then preserved forever in the positions of galaxies. Cosmologists use this scale as a standard ruler. Because we know exactly how long the Baryon scale should be, from our understanding of the physics of the early plasma. We can measure how large it appears at different distances, and use that measurement to determine how much the universe has expanded between then and now. The frozen sound of the Big Bang becomes a measuring tape for the history of cosmic expansion. The first sound the universe ever made is still here, still measuring, still telling us how large everything has become. The hot gas that fills galaxy clusters, heated to millions of degrees by the gravitational energy of matter falling into the cluster over billions of years, leaves its mark on the oldest light in the universe. When the photons of the cosmic microwave background pass through a galaxy cluster on their way to us, they interact with the hot electrons in the cluster's gas. The electrons give the photons a small energy boost, a process called inverse Compton scattering. The photons gain energy. Their wavelengths shorten very slightly, and this leaves a small but detectable distortion in the CMB spectrum as observed in the direction of the cluster, a slight deficit of CMB photons at low frequencies and an excess at higher frequencies. This distortion is called the Sunyaev-Zel'dovich effect, and its strength, parameterized as the Compton Y distortion parameter, is directly proportional to the total pressure of the electrons in the cluster along the line of sight. The higher the electron pressure, the larger the distortion. The more massive the cluster, the more hot gas it contains, the more strongly it marks the CMB. By mapping the Y distortion across the sky, cosmologists can find galaxy clusters even when they are too distant or too faint to see in visible or X-ray light. The hot electrons in those clusters write their presence in the ancient light of the CMB, leaving a shadow we can read from here. The oldest light in the universe, carrying the fingerprints of the hottest places in the universe. Ancient light, marked by extreme heat, still traveling, still carrying the record of everything it passed through. Not everything the early universe tried to build was allowed to survive. The gene's mass is a threshold, a minimum mass that a cloud of gas must exceed for gravity to win against internal pressure and allow the cloud to collapse. Below the gene's mass, pressure wins. The cloud expands rather than contracts. Nothing forms. Above the gene's mass, gravity wins. The cloud collapses. Eventually, something, a star, a galaxy, a halo of dark matter, is born, and the gene's mass is not constant. It evolves with the temperature and density of the universe. In the hot, dense, early cosmos, it was enormous, preventing the formation of very small structures. Then, as the universe cooled and recombination occurred, and the intergalactic gas was freed from the radiation field that had been keeping it warm, the gene's mass dropped dramatically. Small structures could suddenly form. But later, during the epoch of reionization, the gene's mass rose again. As the ultraviolet radiation from the first stars and quasars reheated the intergalactic gas, it raised the pressure in small halos, evaporating or preventing the formation of mini halos, the smallest dark matter structures that might otherwise have hosted tiny galaxies or even the first stars. An enormous number of mini halos that might have formed, small knots of dark matter and gas, each potentially the seed of a tiny galaxy, were suppressed, dispersed, prevented from becoming. The universe's smallest potential structures, erased by the radiation of its first luminous objects before they could fully develop. The universe made things and unmade them, and made other things from what remained. There's a baseline in the universe, a minimum level of warmth in the gas that fills galaxy clusters, regardless of how massive or how old the cluster is. This is the entropy floor, a lower limit to the entropy of the intercluster gas, below which observations never find it, even in the smallest and most recently formed clusters. The gas in clusters is never colder or smoother than a certain level. It always has at least as much thermal energy, at least as much turbulence, at least as much entropy. And the origin of this floor appears to lie in the early universe, before the clusters themselves existed, before the dense gravitational knots of the cosmic web had fully assembled, when the intergalactic gas was still relatively smooth and diffuse. The radiation from early supernovae and from the first quasars and active galactic nuclei poured energy into it, preheating it, raising its entropy above what gravitational collapse alone would produce. This preheating was, in a sense, the universe preparing its gas for what was to come, ensuring that when clusters eventually assembled, the gas they captured was already warm, already stirred, already carrying the energy of those earliest explosive events. As we approach the horizon, the entropy floor rises. The earlier the universe, the closer in time to those first explosive preheating events, and the more strongly the intergalactic gas carries their imprint. Everything that forms is shaped by what came before it. Every cluster inherits the warmth of the universe's first supernovae. Every galaxy forms in gas that remembers its origins. There is a question that seems simple and turns out to be profound. If the universe is infinite, and if it contains an infinite number of stars in every direction, then why is the night sky dark? In an infinite, eternal, unchanging universe, every line of sight would eventually terminate on the surface of a star. The entire sky would blaze with starlight, as bright as the surface of the sun in every direction. There would be no darkness. There would be no night. This puzzle is Olber's paradox, and the resolution of it is one of the deepest things we know about the cosmos. The universe is not infinite in age. It has existed for only 13.8 billion years. Light from stars more than 13.8 billion light years away, and from stars and galaxies whose light has not yet had time to reach us, simply has not arrived. The sky is dark in those directions not because there is nothing there, but because the light has not had time to come. And then there is redshift. Even the light that has arrived from the most distant galaxies has been stretched by the expansion of the universe from visible wavelengths into infrared and microwave, below the threshold of what human eyes or even most telescopes detect in the visible band. The light is there, but it has been diluted and stretched into darkness. These two effects, the finite age of the universe and the redshifting of distant light, together resolve the paradox. The sky is dark because the universe is young, because the universe is expanding, because we are, in a sense, racing away from some of the light before it can reach us. The darkness of the night sky is not an absence, it is a consequence. It is the universe telling us something true about itself. There is a radio hum in the cosmos, not from intelligent sources, not from technology, but from the spiraling of electrons. When electrons move at close to the speed of light through a magnetic field, they spiral around the field lines, and as they spiral, they radiate. This radiation, called synchrotron emission, is emitted at radio wavelengths. And the superclusters and clusters and filaments we pass through are threaded with both relativistic electrons and magnetic fields, which means they are, to a radio telescope, glowing. The electrons that produce this emission come from a variety of sources. Supernova remnants accelerate electrons to relativistic velocities. Active galactic nuclei and their jets produce enormous populations of fast electrons. Shock waves from merging clusters sweep up and accelerate electrons as they collide, and the result is a diffuse radio glow that permeates the large-scale structure of the universe. The synchrotron foreground, the radio buzz of the cosmic web. For radio astronomers try to detect the even fainter signals of the cosmic microwave background or the 21-centimeter emission of neutral hydrogen from the early universe. This synchrotron foreground is a challenge. It must be carefully modeled and subtracted. It sits in front of everything else, buzzing gently. The electromagnetic signature of electrons doing what electrons do when magnetic fields make them turn. The universe is loud in radio. What our eyes see as dark and quiet, our radio instruments hear as a soft, constant, ubiquitous hum. The cosmic microwave background, the ancient, uniform glow of the early universe that fills the sky in every direction, is not perfectly uniform. It has a slight asymmetry. One side of the sky is very, very slightly warmer. The other side is very, very slightly cooler. Not by much. The difference is about 1 part in 1,000 of the total temperature, which is itself only 2.725 degrees above absolute zero. An extraordinarily small difference. But it is there, and it is measurable, and it tells us something. We are moving. The solar system and the Milky Way and a local group are all moving relative to the frame of the cosmic microwave background, moving at approximately 370 kilometers per second in a direction toward a point in the constellation Leo. And because we are moving, the CMB photons coming from the direction we are moving toward are slightly blue shifted, slightly higher frequency, slightly warmer. And the photons coming from behind us are slightly red shifted, slightly lower frequency, slightly cooler. This is the CMB dipole, the Doppler shift of the entire sky, from our own motion through the universe. It was one of the first anisotropies detected in CMB, and it is the largest. It tells us with extraordinary precision both the speed and direction of our motion through the cosmos. We thought we were still. We were always moving. Everything is always moving, and the ancient light of the universe reads our velocity in its temperature. The cosmic microwave background is not a featureless plane. Look carefully enough, with sufficiently sensitive instruments at sufficiently fine scales, and it is covered in tiny fluctuations, slightly warmer patches, slightly cooler patches, variations of 1 part in 100,000 in the temperature of the ancient light. Some of these fluctuations were imprinted directly by the primordial density variations, the seeds of all structure in the universe, set at the very beginning and then frozen into the CMB at recombination. These are the primary Sachs-Wolf fluctuations. But there is another kind. As the CMB photons travel through the universe on their way to us, they pass through regions of varying density. When a photon falls into the gravitational well of an overdense region, it gains energy. When it climbs back out, it loses energy. In a static universe, these effects would exactly cancel. But in an expanding universe, the gravitational wells themselves change while the photon is inside them, and the cancellation is not perfect. When a photon passes through a supervoid, one of the enormous dark, underdense regions we've been encountering throughout our journey, it gains a small amount of energy entering the void and loses a slightly smaller amount leaving it. Because the void has grown during the transit, the net result is a slightly hotter spot in the CMB in the direction of overdense regions, and a slightly cooler spot in the direction of supervoids. The largest and deepest void in the universe are written in the temperature of the ancient light as cold spots. The universe's emptiest places, marked by the faintest of cool shadows and the oldest light we can detect. The void making itself known, the absence leaving a trace. We are approaching the edge now, not the edge of space. Space has no edge we can reach, but the edge of what light can show us, the boundary of the observable, the horizon beyond which we cannot see, not because nothing exists, but because the universe was not yet transparent when the light from beyond it was formed. We are approaching a wall, a surface, the last moment when light and matter were touching before they separated and the universe became clear. And everything beyond that surface, the first 380,000 years of cosmic history, the hot, dense plasma of the very young universe, is hidden from us, not in darkness, but in a fog so complete that no photon of visible light has ever escaped it to reach our instruments. Let us approach it slowly. Let us understand what we are looking at before we arrive. The cosmic microwave background carries 2 kinds of stories. The first is the story of the early universe. The primordial fluctuations in the hot plasma imprinted on the CMB at the moment of recombination 380,000 years after the Big Bang. These fluctuations are the seeds from which all structure grew. They are the oldest signal in the universe. The second kind of story is subtler. It is the story of the journey. The 13.8 billion years the CMB photon spent traveling from the surface of last scattering to our instruments. And during that journey, those photons pass through the evolving gravitational landscape of the universe. through forming and dissolving structures, through voids growing deeper and clusters growing denser, through a cosmos slowly transitioning from matter-dominated to dark energy-dominated. When a CMB photon falls into a gravitational well, an overdense region, a forming cluster, it gains energy. When it climbs back out, it loses energy. In a matter-dominated universe, the potential well would be unchanged during the photon's transit, and the gains and losses would cancel. But as dark energy began to dominate, about 5 billion years ago, the gravitational potential started to decay, structures stopped growing, and the wells became shallower. The photon climbing out found a smaller hill to climb than the one it descended. It emerged slightly hotter than it entered. This effect, the integrated Sachs-Wolf effect, add a faint, large-scale warmth to the CMB in the directions of the largest superclusters, and a faint coolness in the directions of the largest voids. It is a record not of the early universe, but of dark energy's slow takeover of the cosmos, the oldest light in the universe, marked by the newest physics. Ancient photons carrying the signature of dark energy on their faces. We have spoken already of a Compton Y distortion, the way hot electrons in galaxy clusters boost CMB photons to slightly higher energies. But let us pause here and feel the full strangeness of this as we approach the CMB surface itself. Every galaxy cluster we have passed through on this journey has left its mark on the ancient light, not on the light the cluster itself emits, but on the much more ancient light of the cosmic microwave background, which have been traveling through the universe since long before those clusters existed. The CMB photons that are right now arriving at Earth in the direction of a galaxy cluster are not the original, unmodified photons that left the surface of last scattering 13.8 billion years ago. They have been scattered. Their energies have been shifted slightly by the hot electrons in the intracluster gas. They arrive at our instruments carrying the mark of every hot environment they pass through on the way. The surface of last scattering is not a clean, pristine record. It is a document that has been annotated in transit, marked and modified by every structure the photons pass through on their long journey. Clusters, filaments, voids, dark energy, all of them have left signatures, large and small, on the faces of these ancient photons. We read the early universe through 13 billion years of edits. The original text is still there underneath, but the margins are full. There's another background radiation in the universe, less famous in the CMB, but no less profound in what it tells us: the cosmic infrared background. When stars form inside gas clouds, much of the ultraviolet and visible light they emit is absorbed by dust grains in the surrounding cloud. The dust warms up and re-emits the energy at longer wavelengths. In the infrared and across cosmic history, an enormous amount of star formation has occurred inside dusty environments. All of that dust-reprocessed starlight has been accumulating in the universe for billions of years, filling space with a faint, diffuse infrared glow that we can detect as an isotropic background radiation. The anisotropies in this background, the fluctuations in its brightness from place to place across the sky, tell us where the dusty star formation was concentrated, and they peak at redshifts of about 1 to 2, which corresponds to the cosmic noon era we passed through earlier. The universe's peak epoch of star formation was also, by and large, a dusty epoch. Much of the starlight from that era was absorbed by dust and re-emitted in the infrared, and that re-emitted glow persists to this day as the cosmic infrared background. The universe glows in frequencies we cannot see with our eyes. In infrared, in radio, in microwave, everywhere we look, in every wavelength, the sky is bright with the integrated history of everything that ever happened, every star that ever formed, every dust grain that ever absorbed light and gave it back. The universe is luminous in ways our eyes were never designed to register. We are here. This is the surface of last scattering. Not a surface in the physical sense, not a wall or a membrane you could touch or see, but a moment, a boundary in time, spread across all of space simultaneously. That marks the instant when the universe changed from opaque to transparent. Before this moment, in the hot, dense, ionized plasma of the early universe, photons could not travel freely. They were constantly scattering off free electrons, absorbed and re-emitted, bouncing from one particle to the next, unable to travel more than a short distance before interacting again. The universe was a fog, a hot, bright, perfect fog, in which light existed but could not move. And then, 380,000 years after the beginning, the universe cooled to approximately 3,000 degrees. Electrons slowed. Protons and electrons combined into neutral hydrogen atoms. And suddenly, there were no longer free electrons for the photons to scatter off. The fog lifted. The universe became transparent. And the photons that were present at that moment, the photons that had been trapped in the plasma, scattering endlessly, were freed. They have been traveling ever since, for 13.8 billion years, in every direction, filling the universe with the ancient glow of that first moment of clarity. And when they arrive at our instruments, stretched by the expansion of the universe from visible wavelengths into microwaves, we call them the cosmic microwave background. We are looking at the universe's first light, the first photons that were ever free to move, the beginning of sight. Take a moment, let that settle. There is no need to move on immediately. We are exactly where we set out to be. The surface of last scattering is not perfectly smooth. Look closely enough at scales of arc minutes across the sky, and the CMB has texture, fluctuations, slight warmth here, slight coolness there, at angular scales that correspond to physical scales of hundreds of thousands of light years at the time of recombination. These fluctuations are the acoustic peaks, the frozen pattern of the Baryon acoustic oscillations at the moment the sound wave stopped. The compressions of the plasma, which are slightly warmer and denser, appear as slightly warmer patches. The rarefactions, slightly cooler and less dense, appear as slightly cooler patches. The pattern is a direct imprint of the sound waves that were propagating to the plasma right up until the moment they stopped. but at the very smallest scales, the fluctuations are smoothed away. This is silk damping, named for the cosmologist Joseph Silk, who calculated the effect. In the hot plasma of the early universe, photons diffuse from slightly denser regions into slightly less dense ones, washing out the finest fluctuations. Any variation at a scale smaller than the typical distance a photon could diffuse during the epoch before recombination was erased, smoothed, averaged away. The universe's finest texture, the smallest features of the primordial plasma, was blurred before it could be preserved, like a photograph taken slightly out of focus. The large structure survived, the small ones dissolved. What we see is the acoustic pattern, present but softened at the smallest scales. The universe's earliest details, preserved but not perfectly, blurred by the very physics of the plasma itself. The transition from opaque to transparent was not gradual. It was rapid, shockingly rapid by cosmic standards. The Thomson optical depth, a measure of how much scattering a photon undergoes as it travels through a given column of matter, drops by an enormous factor over a very narrow range of redshift around the time of recombination. Before recombination, the optical depth is essentially infinite. Photons cannot travel more than a tiny distance without scattering. The universe is completely, perfectly opaque. Then, over a period of roughly 100,000 years, which sounds long, but is a tiny fraction of the age of the universe at that point, the neutral hydrogen forms. The free electrons disappear, and the optical depth plummets. Photons that were scattering every tiny fraction of a light year can suddenly travel billions of light years without interacting with anything. The universe went from fog to glass in what is, cosmologically speaking, the blink of an eye. This sharpness is why the CMB is so well defined. Because the transition was rapid, the surface of last scattering is a relatively thin shell, not a broad, diffuse region, but a specific, well-defined moment in cosmic history that we can identify and study with precision. If the transition had been slow and gradual, the surface would have been blurred, and the acoustic features we read from it would have been washed away. The universe cleared quickly, and because it cleared quickly, we can read it. Some things the universe erased before we ever had the chance to see them. In the hot plasma before recombination, photons were not merely scattering passively. They were scattering repeatedly and energetically through a process of Compton and Thomson scattering that continuously redistributed their energy and momentum. And this vigorous, constant scattering had a smoothing effect on the finest scale fluctuations in the plasma. Any density fluctuation smaller than the mean free path of a photon, the typical distance between scatterings, was continuously mixed and averaged away. Photons diffusing from warm, dense regions into cooler, less dense regions carried energy with them, diluting the temperature differences. The plasma was, in effect, self-smoothing at small scales. The finest variations in density and temperature were continuously erased by the very scattering that kept the plasma opaque. By the time recombination occurred and the photons were freed, those finest features were gone. Not just faint, gone below the silk damping scale. The primordial fluctuations have been erased as thoroughly as if they had never existed. Whatever tiny structures might have formed from them, whatever small-scale variations might have grown into the universe's smallest galaxies or earliest stars, were prevented from developing by the smoothing action of the plasma itself. The universe's first moments contained information that will never reach us. Features too small for the plasma to preserve. Patterns erased before they could become anything. Some stories are told, some are not. As the universe expands, the photons within it do not disappear, but they change. As the scale factor of the universe, the measure of how large a universe is relative to some reference size, grows, three things happen to the CMB photons simultaneously. Their wavelengths are stretched in proportion to the expansion. Their energies drop in inverse proportion to the scale factor. And the number of photons per unit volume drops as the cube of the scale factor, because the same number of photons are now spread across a larger volume. The result is a universe that cools as it expands. At the moment of recombination, the temperature of the CMB was approximately 3,000 degrees. Today, after 13.8 billion years of expansion, it is 2.725 degrees above absolute zero. The universe is cooled by a factor of roughly 1,000. And yet, the photons are still there. The same photons that were present at recombination, stretched, cooled, diluted, but still there, still traveling, still filling the universe uniformly in every direction. The CMB is the oldest light in the universe and also the coldest. It has been cooling since the moment it was freed, stretched by the same expansion that stretches the space between galaxies. It started as the warm glow of a hot plasma. It will end in the unimaginable far future as the universe continues to expand. As radiation of such low energy that is effectively indistinguishable from absolute zero, the universe's first light, still here, still cooling, still slowly fading. The CMB marks the edge of what light can show us, but it is not the oldest background radiation in the universe. Before the universe was transparent to photons, it was transparent to something else. Neutrinos. Neutrinos interact with matter only through the weak nuclear force, which means they interact very, very rarely in the hot, dense early universe. Even the weak force was strong enough to keep neutrinos in thermal equilibrium with the photons and baryons. But as the universe expanded and cooled, the weak interaction rate dropped below the expansion rate, and the neutrinos decoupled, stopped interacting, and began to travel freely. This happened approximately 1 second after the Big Bang. 1 second before the universe was even a minute old. The cosmic neutrino background that formed at that moment is a sphere around us analogous to the CMB, but larger because it was released earlier when the universe was smaller and the neutrinos have been traveling through the expanding cosmos for longer. It surrounds even the surface of last scattering, enclosing it within a still older, still more ancient shell. We cannot detect it directly with any current instrument. Neutrinos are almost impossible to capture, but cosmologists have measured its effects on the CMB and the large-scale structure of the universe, and they confirm it is there. A sphere of ancient particles, 1 second old, surrounding everything we can see. 1 second after the beginning, and already a horizon, already a limit, already a record. Every particle, every signal, every form of information has its own horizon. The photon horizon, the CMB surface, is the furthest light can show us. The neutrino horizon is slightly further. The sphere defined by how far neutrinos have traveled since they decoupled 1 second after Big Bang. And there's a still older horizon, the gravitational wave background. The imprint of gravitational waves generated in the very first fractions of a second of the universe's existence, possibly from inflation itself. This sphere, if we could detect it, would be the oldest signal the universe has ever produced, from a time so early that all other forms of matter and energy were still a unified plasma. We cannot yet detect the gravitational wave background directly. Our instruments are not sensitive enough, but it is there, surrounding everything. The outermost shell of a series of nested spheres, each one marking the furthest reach of a different kind of information. Photons, neutrinos, gravitational waves. Each one an independent messenger from a different epoch. Each one a different horizon. Each one carrying information that nothing else can carry, from times that no other signal can reach. And beyond all of them, the true beginning, the singularity, or whatever preceded it, the moment before all of this, which lies behind every horizon, unreachable, unsignable, permanently and completely silent. There are depths beyond every depth, horizons behind every horizon. The universe is not just large, it is layered, and each layer we peel back reveals another, older, quieter one beneath. We have come a very long way tonight. We have reached the edge of light. The surface of last scattering is behind us now, or rather, since we cannot truly pass through it. It surrounds us, the furthest wall of the observable universe, the limit of what photons can show us. But the universe does not end here, and neither does this journey, because there are other kinds of edges, other kinds of horizons, limits that come not from the opacity of the past, but from the geometry of the future. And there are signals older than light itself, woven into the fabric of space from the very first moments of inflation, still present, still whispering. If only we had ears fine enough to hear them. Let us move through these final territories, the places beyond what light can reach, the physics of the very beginning, the edges of what can ever, in principle, be known. We have been speaking of the particle horizon as though it were a single thing, a single edge, a single depth beyond which nothing reaches us. But the horizon is not one. It is many. Every kind of signal that travels through the universe has its own horizon, defined by when it decoupled from the primordial plasma and began to travel freely. For photons, That moment was recombination, 380,000 years after the Big Bang. The CMB photons have been traveling since then, and their horizon is the surface of last scattering for gravitational waves from the very early universe, generated during inflation or during phase transitions in the first fractions of a second. The horizon is different. These waves decouple from matter essentially at the moment they were created, because gravitational waves interact with matter so weakly that they effectively travel freely from the beginning. Their horizon is much larger than the photon horizon, much older. They carry information from epochs so early that no electromagnetic signal could ever reach us from them. The two horizons are different sizes, different ages, different depths. The photon horizon shows us the universe at 380,000 years. The gravitational wave horizon shows us, in principle, the universe at fractions of a second old. Two different windows, opening onto two different epochs, using two entirely different kinds of light. The universe has more than one history, and each kind of signal reveals a different chapter of it. The past horizon, the CMB, the surface of last scattering, is a boundary imposed by the history of the universe. It marks how far the oldest light has had time to travel since it was freed. But there is another horizon, a future one, and it is moving because the expansion of the universe is accelerating, driven by dark energy, growing faster and faster over time. There's a distance beyond which space is receding from us faster than light can cross it. Signals from beyond that distance can never reach us. They are already permanently beyond our reach, and this horizon is not fixed. As the expansion accelerates, the horizon moves inward relative to the current distribution of galaxies. Galaxies that are today just inside our observable universe, just inside the sphere of things that could, in principle, send us a signal, will eventually cross the threshold, will eventually recede to a distance where the space between us grows faster than light can cross it. And once they cross that threshold, their light will never reach us again. The most distant galaxies we can currently see are already dimming, already redshifting, already on their way to invisibility. In tens of billions of years, long after our sun has died, long after the Milky Way has merged with Andromeda, the night sky will be darker, fewer galaxies visible, the local group, perhaps, and nothing else. The universe is not becoming more visible. It is becoming less so. The horizon is closing in very slowly as dark energy carries more and more of the cosmos beyond the reach of any signal. What we can see now is more than we will ever see again. What we are losing is not dramatic. It is glacial. It is the slowest kind of loss. Each billion years, the accelerating expansion carries a few more galaxy groups beyond the cosmological horizon. A few more clusters of galaxies that were, until recently, in principle observable, become permanently unreachable. Their light, already old by the time it reaches us, grows more and more redshifted, dimmer and dimmer, approaching but never quite reaching silence, until finally even the most sensitive instruments could not detect it against the background noise of the universe. And with each such loss, a permanent deletion occurs. Those galaxies, their stars, their planets, whatever histories they contain, become not just distant, but fundamentally unknowable. No information from them can ever reach us. No signal, no matter how powerful, no matter how patiently sent. They are gone from our universe, not in the sense of ceasing to exist, but in the sense of ceasing to be reachable. Future astronomers, if there are any, in the deep future of a universe that will be growing darker and emptier with each passing eon, will see a smaller cosmos than we do. We'll have access to less information. We'll be able to observe fewer structures, fewer events, fewer galaxies. We live, in a sense, in a privileged epoch. The universe is still close enough to its active past that we can see evidence of what it once was. The clusters are still there. The CMB is still detectable. The history is still visible. This too will pass. But not tonight. Tonight, it is still all here. Black holes radiate. This is one of the most remarkable predictions of modern physics. Stephen Hawking showed in 1974 that the event horizon of a black hole, the boundary beyond which nothing can escape, is not perfectly black. Quantum effects near the horizon cause pairs of particles to appear spontaneously. One falls into black hole, one escapes. The escaping particles carry energy away from a black hole, and the radiation they produce has a precise thermal spectrum, as if the horizon itself were a warm surface. The temperature is extraordinarily low for any astrophysical black hole, far below the temperature of the CMB for any stellar mass or supermassive black hole. But it is not zero, and for very small black holes, it becomes significant. What is less widely known is that the same physics applies to cosmological horizons. Our own future horizon, the boundary beyond which nothing can ever reach us due to accelerating expansion, also radiates. The de Sitter temperature associated with our cosmological horizon is extraordinarily small, roughly 10 to the minus 30 Kelvin, a temperature so close to absolute zero that it is essentially unmeasurable and practically irrelevant. But it is not zero. Even the boundary of the observable universe glows, ever so faintly, with the quantum warmth of the horizon. The edge of what we can know is not perfectly dark. It radiates at a temperature just barely above nothing into the near-perfect cold of the expanding void. Even the edge of everything is not entirely quiet. Everything we have seen tonight, every galaxy, every filament, every void, every cluster, every star, every planet that might orbit any of the hundreds of billions of stars in any of the 2 trillion galaxies we have passed, all of it came from quantum noise, from the randomness built into the structure of the universe at the very smallest scales, from the unavoidable uncertainty that quantum mechanics writes into every position, every momentum, every field value. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called inflation. The universe grew by an enormous factor, perhaps by a factor 10 to the power of 26 or more, in an incredibly short time. And during this expansion, the quantum fluctuations in the fields driving inflation were stretched. What were microscopic, subatomic fluctuations, random variations smaller than an atomic nucleus, were stretched to cosmic scales, to sizes comparable to galaxy clusters, to the scales at which they could eventually seed the formation of structures. Those stretched fluctuations became the density variations that grew into the cosmic web. The small ones became stars. The larger ones became galaxies. The larger still became clusters. The very largest became the great walls and voids of the cosmic architecture we have been traveling through all night. Quantum randomness, amplified by inflation, became the architecture of the cosmos. The most uncertain, most fundamentally indeterminate aspect of physical reality became the blueprint for everything that exists. Everything you have seen tonight, and everything you cannot see, began as noise. If inflation stretched quantum fluctuations into cosmic seeds, then the shape of those seeds, the statistical distribution of their sizes, their amplitudes, their correlations, carries information about the conditions during inflation itself. This statistical fingerprint is called the primordial power spectrum. It describes how much fluctuation existed at each physical scale, and its shape, which is nearly, but not exactly, the same at all scales, with slight deviations that cosmologists measure with extraordinary precision, tells us about the nature of the inflationary process. The primordial power spectrum is very nearly, but not exactly, scale invariant. It is slightly tilted, slightly more power at large scales than small scales. This tilt, measured precisely by CMB experiments, is called the spectral index, and the specific value of that tilt, the specific shape of any deviations from perfect scale invariance, constrain which models of inflation are viable. At the very highest and very lowest scales, the power spectrum may show turnovers, places where the nearly uniform distribution of power bends and changes. These turnovers, if detected, would correspond to features in the inflationary potential itself. Moments during inflation when something happened, when the energy landscape changed, when the conditions of the very early universe left a specific mark on the distribution of all subsequent structure. The shape of the universe's largest structures encodes the physics of its first moment. The web we have been traveling through is a record of inflation itself. In the very earliest universe, in the first fractions of a second, before even the quarks had organized themselves into protons and neutrons, the universe underwent a series of phase transitions, moments when the fundamental forces, which in the extreme heat of the earliest cosmos had been unified into a single interaction, separated, when the electroweak force split into electromagnetism and the weak nuclear force, when the strong force separated from the rest. These transitions were not instantaneous and uniform. They proceeded by nucleation, bubbles of the new phase forming and expanding and colliding like bubbles in boiling water, at temperatures and densities that make any earthly comparison inadequate. Those colliding bubbles, those churning phase transition fronts, generated gravitational waves, ripples in the fabric of space-time, propagating outward at the speed of light, carrying energy from those earliest violent events. And those gravitational waves are still there, still propagating, still filling the universe with a stochastic background. A random noise of space-time ripples from the very first moments of creation. We cannot yet detect this background. Our gravitational wave instruments are not sensitive enough. But the next generation detectors, space-based interferometers, pulsar timing arrays, future experiments whose scale dwarfs anything yet built, may reach the sensitivity needed to hear it. The first sound of the universe, still reverberating in the structure of space itself. A hum so ancient and so faint that we have only just begun to build the ears to hear it. Light can be polarized. The CMB is polarized. The polarization of the CMB, the preferred direction of the electric field oscillations in the ancient photons, can be decomposed into two mathematical patterns. E modes, which have no curl, like the gradient of a scalar field, and B modes, which do curl like the rotation of a vector field. Density fluctuations, the acoustic oscillations, the seeds of structure, produce only E-mode polarization. They cannot, by their nature, produce B modes. But gravitational waves, the tensor perturbations generated during inflation, rippling through the primordial plasma at the moment of recombination, produce B modes. Unique, distinctive, curling patterns in the polarization of the CMB that no density fluctuation could mimic. If primordial gravitational waves from inflation are present at sufficient amplitude, they should leave a B-mode signal in the CMB polarization that we can, in principle, detect. The detection of this signal will be the most direct evidence we can hope to gather about what happened during inflation, about the energy scale at which it occurred, about the nature of the inflationary field. It would be, essentially, the direct detection of the gravitational wave background from the very first moment of the universe, a signal older than light, a fingerprint of inflation itself, written in the polarization of the oldest electromagnetic radiation in existence. We have not yet definitively detected it, but we are looking somewhere in the universe at cosmological distances billions of light years away. Something releases an enormous burst of radio waves a fraction of a second, a flash of electromagnetic energy so intense that it can be detected across the observable universe with a radio telescope, lasting perhaps a millisecond and then gone. These are fast radio bursts. Their origin is still debated, though evidence points toward highly magnetic neutron stars, magnetars, releasing energy in intense outbursts. Whatever their source, they are extraordinarily useful to cosmologists because radio waves of different frequencies travel through ionized gas at slightly different speeds. Lower frequency waves are slowed more than higher frequency waves, and the difference in arrival time between the lowest and highest frequency components of a fast radio burst, the dispersion measure, depend precisely on how much Iona's gas the burst passed through on its journey to us. By measuring the dispersion measure of a fast radio burst and combining it with measurement of its distance, cosmologists can determine the average density of Iona's gas along that particular line of sight. They can probe the diffuse intergalactic medium that fills the space between galaxies, the wind we encountered earlier, the warm, hot gas of the cosmic filaments, with precision that no other technique can match. Each fast radio burst is a probe, a momentary flash that illuminates, in its passage, everything between its source and us. The universe uses its own signals to measure itself. The most energetic single events in the observable universe last only seconds. Gamma ray bursts, releases of gamma ray energy so intense that a single burst can, for its brief duration, outshine the entire observable universe in gamma rays. They arise from two known types of cataclysm: the collapse of a massive star into a black hole, in which the collapse drives two polar jets of material outward at nearly the speed of light, producing gamma rays as the jet punches through surrounding stellar material, and the merger of two neutron stars, a violent coalescence of two of the densest objects in the universe, spinning together and colliding, also driving jets, also producing a brief, brilliant gamma ray flash. After the burst itself, the jet continues to expand to the surrounding interstellar and intergalactic medium, producing an afterglow, a slowly fading emission at X-ray, optical, and radio wavelengths that can persist for days or weeks after the initial flash. This afterglow is scientifically rich. By studying how the afterglow fades, its light curve, its spectrum, the way different wavelengths dim at different rates, cosmologists can reconstruct the physics of the jet, its energy, its geometry, the density of the medium it is expanding into, the processes of particle acceleration at the shock front between the expanding jet and the surrounding material, extreme physics, visible across billions of light years, lasting only seconds, leaving an afterglow that is a perfect natural laboratory for the most energetic particle physics in the observable universe. The most violent things in the cosmos are also among its most informative. The universe teaches us its extremes through its extremities. We are in the deepest territory now, past the galaxies, past the CMB, past the neutrino horizon. The universe around us is not the universe of observation. It is the universe of possibility, of theory, of the things that might exist in the dark, that physics permits and perhaps predicts, but that we have not yet found or perhaps cannot find. What is a universe made of in its most hidden layers? What relics of the earliest moments might still be drifting through the dark, unseen? And what is the shape of all of this, the geometry of the whole? Let us move through these last speculative territories with the same patience we have brought to everything else. These questions are not resolved. They are open, and open questions, held gently, without urgency, are among the most restful things there are. When a star explodes, when it reaches the end of its life in the violent, luminous death of a supernova, the light from that explosion travels outward in all directions at once. Some of that light travels directly toward us, arriving as the initial flash that astronomers detect and study. But some of the light travels in other directions first, strikes dust clouds and surrounding interstellar medium, and is reflected back toward us. This reflected light travels a longer path, out to the dust cloud and back, and so it arrives later, sometimes much later, months, years, decades. When this delayed, reflected light arrives, it appears as a ring, a circle of faint illumination expanding outward from the position of the original explosion. The ring is the intersection of a sphere of light, the expanding wavefront of the original flash, now reflected with the plane of the sky. As time passes, the ring grows larger as our line of sight intersects successively more distant portions of the dust shell. This is a light echo, and it is extraordinarily useful. By measuring the geometry of the echo, its size, its rate of expansion, its distance, astronomers can reconstruct the three-dimensional distribution of dust around the original explosion, mapping structures that are too faint and too diffuse to observe directly. The supernova is long since faded. The light from its death has moved on, but its echo lingers, slowly expanding to the dust, still carrying information about the explosion that created it, still arriving, still being read. Old light, arriving late. The universe's patient record-keeping. The early universe was dense, extraordinarily, incomprehensibly dense, and in regions of unusual density, where the fluctuations in primordial plasma were large enough. The matter may have been compressed directly into black holes, not from the collapse of stars, from compression of matter itself. In the first fractions of a second of a universe's existence, these are primordial black holes, and if they exist in significant numbers, they could be drifting through the universe right now, through the voids, through the filaments, through the dark spaces we have been traveling. Primordial black holes could range in mass from extremely small, less than the mass of an asteroid, to very large. The smallest ones would have evaporated by now via Hawking radiation. But black holes above a certain mass threshold would have survived to the present day, still drifting through the universe, invisible, interacting only gravitationally. They are a candidate for some or all of the dark matter. If primordial black holes of certain masses are sufficiently common, their total mass could account for the gravitational effects we currently attribute to dark matter, without any exotic new particle physics being required. We have not confirmed their existence. We have not ruled it out. The darkness around us may be dotted with ancient compressions of the primordial universe, drifting silently through the void, waiting to be found. The dark is patient. It keeps its secrets well. The axion is a hypothetical particle. It was proposed in the 1970s to solve a problem in particle physics having nothing to do with dark matter. But shortly after a proposal, physicists realized that if axions exist with the right mass and properties, they would have been produced in enormous quantities in the early universe and would contribute significantly to the dark matter. Axions are extraordinarily light, far lighter than any other proposed dark matter particle. And because they are so light, they behave differently from heavier dark matter candidates. In the early universe, axions would have formed not as individual particles distributed smoothly through space, but as oscillating fields, coherent quantum states spanning enormous volumes. As the universe evolved, these axion field configurations would have fragmented into compact, dense clumps called axion mini-clusters. Not galaxies, not halos, something much smaller. Dense little balls of axion dark matter, perhaps the mass of a small asteroid, scattered throughout the universe in enormous numbers. If axion mini-clusters exist, the voids we've been traveling through might be peppered with them, not lit up, not detectable by any optical instrument, simply present in the dark, drifting through the emptiness that seems to contain so little. The void, once again, less empty than it seems. The darkness, perhaps full of things too small and too faint and too weakly interacting for any current instrument to reveal. When the universe cooled from its extremely hot early state, the fundamental forces separated from one another in a series of phase transitions. And in some theories of how that separation occurred, defects were produced at the transition boundaries, places where different regions of space, which had independently chosen different directions for the symmetry-breaking field, met at their interfaces. One type of such defect, predicted by many grand unified theories of particle physics, is the magnetic monopole, a particle with a single magnetic pole just north or just south, rather than the paired north-south dipoles of every magnet we have ever observed. A single isolated magnetic charge, stable, massive, and essentially indestructible. The problem, historically, was that standard calculations predicted these monopoles would have been produced in enormous quantities in the early universe, so many that their total mass would have exceeded the observed density of the universe by many orders of magnitude. This monopole problem was, in fact, one of the motivations for proposing inflation. Inflation solved the problem by diluting the monopoles. The rapid expansion stretched the universe so dramatically that any monopoles produced before or during inflation would be diluted to an almost vanishing density, one per observable universe. Perhaps none, but perhaps not quite none. If any monopoles survived inflation or were produced after it, they might still be drifting through the universe somewhere, ancient relics of a broken symmetry, stable forever, still moving very slowly through the dark. Among the candidates for dark matter is a particle called the sterile neutrino, heavier than the ordinary neutrinos we know, and interacting even more weakly with ordinary matter, hence sterile, meaning it does not interact via the weak nuclear force at all, only through gravity and a tiny, indirect mixing with ordinary neutrinos. Sterile neutrinos, if they are the dark matter, would be essentially invisible, but they are not perfectly stable. Over very long time scales, a sterile neutrino can spontaneously decay into an ordinary neutrino and a photon, a single X-ray photon of a specific energy determined by the mass of the sterile neutrino. This decay is extraordinarily rare for any individual particle. But if sterile neutrinos are the dark matter, There are an almost incomprehensible number of them in the universe, and the combined emission from all of them, accumulated across cosmic scales, will produce a faint, diffuse X-ray background, a glow at a specific wavelength coming from the dark matter itself. From every direction in the sky, astronomers have searched for this signal. There have been tantalizing hints of featuring the X-ray background at around 3.5 kiloelectron volts, reported by several independent groups, that does not correspond to any known astrophysical emission line. Whether this is sterile neutrino decay or something else remains unresolved. The dark matter may be glowing very faintly in X-rays right now. We may already be seeing the light of its slow decay. We are not yet certain. The same symmetry-breaking transitions that might have produced magnetic monopoles could also have produced a different kind of defect, a one-dimensional one, a cosmic string, a topological defect, a line-like region of space where the symmetry-breaking field was unable to relax to a uniform value, trapped in an unstable configuration by the topology of the surrounding field, like a crease in a sheet that cannot be smoothed out without tearing the sheet. Cosmic strings, if they exist, would be extraordinary objects, incredibly thin, far thinner than an atomic nucleus, but enormously massive per unit length, potentially millions of billions of kilograms per meter, and under tension, vibrating and oscillating, and losing energy by emitting gravitational waves as they intersect and loop. They would extend across cosmic scales, perhaps across the observable universe, perhaps looping back on themselves in enormous oscillating loops that gradually shrink as they radiate away their energy in gravitational waves. We have not found them. The CMB shows no clear evidence of their gravitational effects on the distribution of structure, but the constraints are not yet tight enough to rule them out entirely. They may exist, threading the dark between galaxies, too thin to see and too diffuse to detect in any survey so far conducted. The universe may be sown through with scars we cannot find. If the symmetry-breaking field that produced cosmic strings can create one-dimensional defects, it can also, under different conditions, create two-dimensional ones. Domain walls, flat, two-dimensional surfaces, potentially of cosmic extent, that separate regions of space where the symmetry-breaking field settled into different stable states, like the walls between magnetic domains and a piece of iron, where regions of different magnetization orientation meet at their boundaries, but at cosmological scales and with cosmological energies. The energy density stored in the domain wall would be immense. A wall of even modest surface density, extended across cosmological scales, would contribute an enormous amount of energy to the universe, potentially distorting the expansion history in ways that will be detectable. This is the problem with domain walls. If they exist and formed in the early universe, they would almost certainly have over-dominated the energy budget of the cosmos, preventing the universe from evolving into anything resembling what we observe. Their absence from our observations is, in a sense, evidence that the symmetry-breaking fields of the early universe were arranged in ways that did not produce them or produce them in configurations that inflated away before they could cause trouble. But in some models, small domain walls could survive, could still be present in the universe today. Thin sheets of concentrated vacuum energy, floating through the dark, invisible to any electromagnetic observation. The walls between different kinds of nothing, still present, still carrying their ancient energy, separating states of vacuum that differ in ways we do not yet understand. Some theories of physics propose that the universe has more than 3 spatial dimensions, not in the sense that we can travel into them, but in the sense that they exist curled or compactified at scales too small to detect directly, woven into the fabric of space-time at every point. Their presence would produce observable effects, not as additional directions we could move in, but as modifications to the behavior of gravity and other forces at short distances. In Kaluza-Klein theories, among the earliest proposals for extra dimensions dating back to the 1920s, the compactification of extra dimensions produces a series of massive particles called Kaluza-Klein modes, which are essentially the higher harmonics of quantum fields propagating in the extra dimensions. These particles will be very massive and very short-lived, but in the extreme conditions of the early universe, they could have been produced in significant quantities. And if extra dimensions exist and have even the slightest effect on gravity at large scales, if gravity leaks even fractionally into the extra dimensions, then the paths of particles moving through the universe, the geodesics of space-time itself, might be very subtly modified, not enough to have been detected in any current observation, but enough, in principle, to be measurable with future instruments. The universe we travel through might be the surface of something larger. Our path through it, perfectly straight from inside, may be curved from outside in ways we cannot yet feel. The universe, as best we can measure it, is very close to spatially flat. Parallel lines stay parallel. The angles of triangles sum to exactly 180 degrees. Space does not curve back on itself in any obvious way. But flatness of curvature does not determine the topology of space. A flat piece of paper, rolled into a cylinder, is still locally flat. Parallel lines still stay parallel. Triangles still have 180-degree angles, but it is globally connected in a different way than an infinite plane. Travel far enough in one direction, and you return to where you started. The universe could, in principle, have a non-trivial topology even if it is perfectly flat. It could be a torus, connected in 1, 2, or 3 directions, so that traveling far enough in any connected direction brings you back to your starting point. If this were the case, and if the universe were small enough, we might see ghost images of our own galaxy in the deep field, the Milky Way as it appeared billions of years ago, arriving from the opposite direction. Cosmologists have searched for such patterns in the CMB. If the universe is smaller than the horizon and connected in this way, the CMB should show repeating patterns, the same fluctuation appearing in multiple places in the sky from different directions. They have not found convincing evidence. The universe, if it loops back on itself, does so on a scale larger than we can currently probe. but the possibility remains. Our journey outward might, in principle, be a journey inward. The edge might be home. Among all the possible geometries that space could have had, the universe chose the flattest one, or very nearly. Measurement of the CMB, of the large-scale structure of galaxies, of the geometry of Baryon acoustic oscillations, all of them converge on the same answer. The spatial curvature of the universe is consistent with zero to an extraordinary precision within the measurement uncertainties. It is indistinguishable from perfectly flat. In a flat universe, the rules of Euclidean geometry hold on the largest scales. Parallel lines stay parallel. The angles of a triangle sum to 180 degrees. Light travels in straight lines that never curve back on themselves due to the overall geometry of space. This flatness is, in a sense, predicted by inflation. The rapid expansion of the early universe would have smoothed out any initial curvature, driving the spatial geometry toward flatness in the same way that blowing up an enormous balloon makes its surface appear flatter and flatter to any observer sitting on it. Whatever the initial curvature of the universe was, whatever was born with, inflation drove it toward zero. And so we find ourselves at the end of this long journey, in a universe whose geometry is the quietest and most straightforward possible. Not curved, not closed, not looping back, just flat, just open, just extending outward in all directions, parallel and infinite, carrying its web of galaxies and voids and ancient light into a future that has no edge. The simplest geometry, the deepest quiet, the most open possible space. We have come as far as we can go, past the galaxies, past the CMB, past every horizon we can reach, past speculation itself, to the very final edges of what physics permits us to imagine. And now, at the furthest point, we can begin the slow, quiet return, not by retracing our path. There is no path to retrace in this journey of thought, but by letting ourselves settle, by allowing all the distances we have covered to rest alongside us in the quiet dark. These last 6 facts are the furthest things we can think, and then, after them, we will rest. In the mathematics of general relativity, there exists a solution that describes something extraordinary, a wormhole, a tunnel through space-time that connects 2 distant regions directly, bypassing the space between them. If such a structure existed, you could, in principle, enter one mouth of the wormhole and emerge in the other mouth billions of light years away, instantaneously, without ever having traveled to the intervening space. You could bypass the horizon. You could step from here to a place beyond the observable universe in a single step. But there are problems, enormous, fundamental problems. For one, the mathematics of wormholes require exotic matter, matter with negative energy density, which violates the energy conditions that ordinary matter satisfies, and which we have never observed and do not know how to create. For another, even if a wormhole could be constructed, it would almost certainly collapse too quickly for anything to pass through it unless it were somehow stabilized, again by exotic matter or by some mechanism we do not understand. And most troublingly, wormholes that allow travel between distant points also, under certain configurations, allow travel backward in time. They permit closed time-like curves. They raise the possibility of paradoxes, of effects preceding their causes, of timelines looping back on themselves in ways that violate causality itself. The universe may not permit such shortcuts. The laws of physics may forbid them, not by explicit prohibition, but by making conditions for their existence impossible to satisfy. And so we are left with the long way, the slow way, the only way that does not require us to tear the fabric of reality. If inflation occurred once, in the first tiny fraction of a second of our universe's existence, it may still be occurring elsewhere in models of eternal inflation. The inflationary field does not stop inflating everywhere at once. It stops in certain regions, bubbles that nucleate within the inflating background and expand outward at the speed of light, each bubble becoming a pocket universe with its own physical laws, its own constants, its own history. Our observable universe would be one such bubble, and beyond our horizon, the inflation that stopped here 13.8 billion years ago may still be running, producing more bubbles, more universes, in an endless, self-perpetuating cascade. If this is true, then our observable universe is not the whole universe. It is one bubble among an infinite number, and the space beyond our horizon is not empty. It is filled with other bubbles, other universes, each causally disconnected from ours, each evolving according to its own rules, each completely and permanently unreachable. We will never see them. We will never detect them. They are not hidden in our universe. They are outside it, beyond the edge of what expansion allows us to reach. Other bubbles, drifting in eternally inflating foam, each one an entire cosmos, each one as real as ours, each one forever beyond the possibility of contact. The edge of our universe might be the boundary between our bubble and another, and we will never know. We spoke of this earlier, but let us return to it now, at the end. Let it settle in the quiet. If the universe is infinite, if it extends without limit in all directions, then every possible configuration of matter must occur somewhere. Not might occur, must occur. The mathematics is unavoidable. Somewhere unimaginably far beyond our horizon, there's a region of space where the matter is arranged almost exactly as it is here. A galaxy very much like the Milky Way, a solar system very much like ours, a planet blue and quiet, with continents and oceans arranged in nearly the same way. And on that planet, in a room very much like the one you are in, someone very much like you, listen to something very much like this, growing still, growing quiet, approaching sleep. They are not you. The separation is so vast that no signal from here will ever reach them. No light, no gravitational wave, no information of any kind. They are beyond every possible horizon, but they are there. The mathematics insists. You are not alone in the infinite. You are mirrored at distances so large that the mind cannot hold them, in regions of space that will never know you exist. And somewhere they are resting too. Somewhere they have already fallen asleep. Somewhere they are still listening. Somewhere they are exactly where you are at exactly this moment, feeling exactly what you feel. Let that thought be whatever it wants to be. Strange, comforting, unsettling, true. Let it rest alongside everything else. Distance is not a single thing in an expanding universe. There is physical distance, the actual separation between 2 points in space at a given moment. And there is moving distance, the distance between those same points if you factor out the expansion of space itself, the distance they would have if the universe stopped expanding and you could measure the gap directly. Some regions at the very edge of the observable universe, regions whose light is just now reaching us after traveling for 13.8 billion years, are in moving coordinates closer to us than the center of the Milky Way. This is because those edge regions were very close to us when the universe was young and small. The light that left them then has been traveling through the expanding universe ever since, and the expansion has stretched the space between us to enormous physical distances. But in the coordinate system that accounts for that expansion, they remain nearby. Moving distances, in a sense, the distance things were separated at the beginning, before expansion carried them apart. And by that measure, the farthest things we can see were once almost within reach. Everything was close once. Everything was nearly touching. And the expansion has been carrying it all apart ever since, stretching the space between every point and every other point, so that what was once close is now impossibly far. Distance is a story. The expansion writes it slowly. And we are reading it from the middle. The early universe was different. In the hot, dense plasma of the first few 100,000 years, dark matter made up approximately 25% of the total energy density. Ordinary matter, baryons, the stuff of stars and planets, contributed about 5%, and the rest was radiation, photons, and neutrinos, which dominated the energy budget in those earliest times. But as the universe expanded and cooled, the radiation diluted away faster than the matter. Photon number density drops as the cube of the expansion, and their energy's redshift. So the total energy density of radiation drops as the fourth power. Matter densities drop only as a cube. And so, over time, the universe transitioned from radiation-dominated to matter-dominated, and then, eventually, to dark energy-dominated, near the horizon. In the regions of the universe we observe from the earliest times, dark matter is less dominant than it is nearby. The universe at recombination was still in the transition between radiation-dominated and matter-dominated. The dark matter was there, shaping the gravitational potential wells into which ordinary matter would eventually fall. But it was not yet the overwhelming component it would become later. We look back in time and see a universe that was less dark, a cosmos where the balance of energies was different, where radiation still mattered, in a way it no longer does today. At the very edge, at the furthest reaches of observation, the universe is becoming something else. Dark energy. The mysterious component that makes up roughly 70% of the total energy density of the universe today, and whose nature we do not yet understand, is growing in dominance as the universe expands. Because dark energy does not dilute, its density remains constant even as space expands. And that means that as matter and radiation dilute away, dark energy becomes proportionally ever more dominant. In the deep future, trillions of years from now, dark energy will be everything. Matter will have diluted to near nothing. The galaxies will be isolated island universes, separated by voids so vast that no signal from one can reach another. And the expansion, driven entirely by dark energy, will accelerate without bound. But that is the future. Tonight, we are concerned with the edge of the present. And at the edge, we already see the beginning of this transition. The matter density near the horizon is lower than nearby. The dark energy density is the same everywhere. And so, at the edge, dark energy is already becoming the dominant force. The universe's future is written at its edges. The emptiness is coming. The acceleration is permanent. The expansion will not stop, and the horizon will keep receding slowly, carrying more and more of the cosmos beyond our reach, into the dark where dark energy is the only thing left. This is the furthest thought, the final edge, the end of what we can see, and the beginning of what will never be seen. We have arrived. And now we rest. We've been gone a long time. We have traveled further than any distance you could walk. Further than light could travel in a human lifetime, or 1,000 human lifetimes, or all the human lifetimes there have ever been. We have moved through galaxies and voids, through the cosmic web, through the CMB, through horizons of light and sound and gravitational waves, all the way to the furthest edge of what can be known. And now we are here, wherever here is, in the quiet, in the dark, in the soft weight of your own body, resting wherever you are resting. The universe is still out there, still vast, still turning. The galaxies are still drifting through their filaments. The voids are still expanding. The CMB is still glowing, faint and ancient, in every direction. The dark energy is still pushing everything apart, slowly and permanently, into a future we cannot see. But you do not need to hold any of it. You do not need to remember the numbers or the names or the distances. You do not need to understand. You were never asked to understand. All you needed to do was travel. And you have traveled. And now you are done. The drone is still here. It has been here the whole time. Low and steady and constant, beneath everything. It will stay as long as you need it to stay. It will hold the space while you rest. Let your breathing settle. Let your thoughts, if there are any left, drift without following them. Let the distances we have covered become part of the dark around you. No longer something to think about, just a quiet presence, a memory of vastness, resting alongside you in the stillness. You are very small, You have always been very small, and that is not a problem. That is a condition. That is the gift. To be small in a vast universe is to be held by it. To be a single point in an infinite space is to be exactly where you are meant to be, at the center, always at the center, surrounded in every direction by the same ancient light, the same deep dark, the same slow expansion carrying everything outward into a future that is patient and kind. We're going to stay here for a while, in the quiet, in the dark. The journey is over. There's nowhere else to go. Nothing left to see. Only this. Only now. Only the soft, steady hum of the universe, and the weight of your own stillness, and the gentle, unhurried drift towards sleep. You are safe. You are still. You are exactly where you are meant to be. And when you are ready, not now, but when you are ready, you can let go entirely. Thank you for traveling with us tonight. Rest well